Good morning, everyone. Let's start today's session. So to introduce and welcome you, let me now introduce Rifna, who is our coordinator. Over to you, Rifna.
A warm good morning to one and all present in this session. We are here today for the 11th edition of the workshop on excitement of research. To take you through this workshop, a few eminent teachers at IIIT Hyderabad would be engaging you with some new topics in different domains. To inaugurate this workshop and to introduce to you about the larger objectives and nuances of doing research, we have with us the Director of IIIT Hyderabad, Professor PJ Narayan, the Dean of Research and Development, IIIT Hyderabad, Professor C.V. Jawahar, and Academic Director of iHub-Data, Professor U. Deva Priyakumar. For the benefit of everyone gathered here, the audience is primarily the best of lot from our technical institution in India, who have shown interest in taking up research internship this summer. A total of over 6,200 students appeared for the first screening examination of Srishti 23, Summer Research Internship for Technological Innovations 2023. To welcome you all to this workshop, we have with us Professor U. Deva Priyakumar, Academic Director of iHub-Data, who also heads Center for Computational Natural Sciences and Bioinformatics, CCNSB at IIIT Hyderabad. Professor Deva Priyakumar received his PhD degree from Pondicherry University, Indian Institute of Chemical Technology, followed by a postdoctoral fellowship at University of Maryland at Baltimore. For his significant contributions in computational chemistry to study reaction mechanisms and biological interactions, Professor Deva has been awarded with prestigious citations like Gold Medal from Chemical Research Society of India, Distinguished Lectureship from Chemical Society of Japan, Google Impact Scholar Award, Young Scientist Medal from Indian National Science Academy, Fellowship from Japan Society for Promotion of Science, and Innovative Young Biotechnologist Award. Over to you, sir.
Yeah, thank you, Rifna, for the kind introduction. So, hello everyone, good morning. Maybe, if you don't mind, if some of you, we don't want to force, but if some of you can turn on the cameras, it would be nice, at least for the first session, right? So, before I start, firstly, I would like to, welcome Professor PJ Narayan, who is our Director of IIIT Hyderabad, and also Professor C.V. Jawahar, who is the Dean of Research at IIIT Hyderabad. Right. So, in addition to that, I also would like to welcome all of you to this exciting day of talking about research. Right. So, I don't want to take too much time, but the idea is that a lot of us are excited about research. Right. So, when we are doing research, whether it's faculty members or students or scientists here at IIIT, we're all excited about doing something new, coming up with solutions or technologies that will make an impact academically or, societally, or, in terms of coming up with new products, for a better future, right? So we are all excited about it. So the idea today is that, we will share this excitement, right? It's not necessarily to excite you in that sense, but we will share this excitement. In that process, we hope that some of you will, get excited, at least, consider research as an option for your career, right? So, I'm assuming most of you, or I know that most of you are undergraduate students in engineering, right? So you're doing BTech, or some of you masters possibly, right? So, you must be thinking, what you would like to do next, right? What kind of companies you would like to go and work with, or what kind of higher education you would like to pursue, right? So in that sense, if you take IIIT Hyderabad, we have a large number of undergraduate students, like the BTech students, and then we also have what we call dual degree students who do both, BTech and masters as an integrated kind of program. And we have more than 50% of the students on campus who are involved in research at one point or other. Right? I would say 100% if you consider all kinds of projects, right? So that way, what we want to do today is to talk a little bit about, what is research, why we do what we do, right? And what are the possible, ways you, enhance your career or growth in the future and so on, right? So in the process, we hope, you consider, as I said before, consider research as a viable option. In that process, some of you, I hope, some of you will be here in IIIT Hyderabad over summer doing your internships. We'll be spending time with some research groups. You will spend, get mentored by other research members and faculty members and so on. Right, so that would be the next step, and I hope in 1 or 2 years from now, a significant number of you will actually join us in our pursuit towards world-class research. Right, so that's the idea. But before I stop, I want to quickly introduce iHub-Data. Right, so we have an entity within IIIT Hyderabad which does a lot of work in data-driven technologies, right? So when we say data-driven technologies, when you have large amounts of data, I'm sure you're seeing a lot of news about several things these days about how AI is, kind of transforming several areas, right? The recent one which makes a lot of news is ChatGPT, for example, right? So in that sense, our one of the our major efforts is in coming up with large amounts of data in specific domains, and then develop solutions that will, develop technologies that will give viable solutions for, better, better lives, right? Whether in terms of healthcare or road safety and automobiles and so on in different areas, right? So we also do a large, skill development programs. The Shristi, for example, is an effort within iHub-Data where we support 100+ students towards their research experience over the summer and possibly to continue also, right? We also have, beyond that, we have support for master's program and PhD program and so on, right? So I don't want to take too much time. If you want more details, you can always reach out to Dr. Raju or anyone of us, and we'll be able to give beyond what is there in the website already. So with that, I will stop, and I again welcome all of you for this exciting day of talking about research. Yeah, thank you.
Yes, thank you so much, sir. Now, to inaugurate this 11th edition of workshop on excitement of research, we have with us Professor PJ Narayan, the director of IIIT Hyderabad. Professor PJ Narayan is a 1984 UG alumnus of IIT Kharagpur, from the first generation of computer science graduate engineers of our country. Professor PJ Narayan completed his MS and PhD in computer science from University of Maryland, US in 1989 and 1991, respectively. Professor PJ Narayan worked in US for over 5 years, after which he worked at the Center for AI and Robotics at DRDO Bangalore till 2000. From 2000 onwards, Professor PJ Narayan has been with IIIT Hyderabad, initially as the head of Center for Visual Information Technology and later as the Dean of Research till 2013. For the last 10 years, Professor PJ Narayan has been the director of IIIT Hyderabad, playing a stellar role in leading disruptive technologies on many fronts. Over to you, sir.
Thanks, Mithuna, for the overly kind introduction. So good morning to all you students, participants of this excitement of research workshop. This is a important day for IIIT. Many years ago, we used to conduct this physically. We used to have hundreds of students come here and for a weekend and spend 2 days listening to these things. Now, of course, this is the era of online, and the advantage, of course, is we can reach out to students like you who are from far away from Hyderabad. But those who are coming were Hyderabad and around those days. So research is about solving, finding answers to unstructured problems. It is not, people have a misconception about research being some solitary affair, sitting somewhere you're growing long hair, beard, getting frustrated, and then some jumping out of the bathtub and running Eureka. I mean, all these stereotypes are there. They are all just stereotypes. There are thousands and thousands of people who engage in research, and that's the reason why we have our technology enhancement every day. I mean, if you had no phones or no mobile phones, certainly 25 years ago, and today you can't live without mobile phone. So many things have gone into it. And we look at in the mobile phone, there is this wonder app called the Google Navigator that all of you know, Maps Navigator. If you go from today, nobody even remembers how to go from place A to place B. They just ask Google and Google will tell you. And remember, think of it, how much technology, what all technology has gone into that, building that product. Of course, the hardware of, such a tiny and very powerful hardware that you carry in your hand, the phone, that is certainly, huge. And to get hardware, get chips smaller and smaller, you need so much physics. You need so much material, so much chemistry to make it all happen. Batteries, and then all the, it's crazy when this started. We all remember obviously life before Google. At least our generation, my generation, definitely remembers navigating maps using physically printed maps. Suddenly, when the GPS-enabled phones come, and you sit in the car, and you take a wrong turn or something, it immediately knows where you are and it corrects you. It seems like a great feature, but at that point, I remember this is not good. Somebody is watching me and doing this. I don't like this. You take a wrong turn, it doesn't scold you, of course. It doesn't say what a fool you are. It says rerouting, and then finds a different way. The idea that at every second somebody up there knows where you are is a little bit unsettling. Of course, now we are used to all that. But then there are so many algorithms that go into finding the best path of the time. I mean, that day, that time, how to go from place A to place B. And then this dynamic rerouting. This is wonder. I mean, this is one product that really has all the hardware advances we have seen in these years, all the software advances, all the human factors that what do people know, and that building products with such all-round understanding, that is the true purpose of research. It is not to push one paper or add one more thing in your resume. It is to produce this product. And all of us, and certainly all of you, the young people, are definitely driven by doing things that are not routine. I mean, that's the whole motto of the youth, that you want to be different. You want to do things which obviously benefit to others, but also things that are your own, not just get a degree, get into a job, do that in a strict pipeline manner. This is what society may expect, but I think you should go beyond that. I remember one of our very early students. The student said, very early student, I think 99 BTech entry student at IIIT Hyderabad, the second batch of IIIT Hyderabad. He told me later, when he came here, this is 99, IT revolution was just obviously happened, but not, the scale was very much smaller. So he said, when he joined IIIT, my goal was to get a job in TCS, after get a BTech degree in IT, whatever, get a job in TCS. Then first year we taught them, lots of stuff. Our IIIT first year BTech curriculum is very different. You get into the subject very early. You get into doing things by hand. At the end of first year, he said, no, TCS, no good. I want to really build products. I want to get a job in Microsoft. Okay, so he was into Microsoft product companies. Then second year, actually, we really get our students into subject area, not just computer programming and the basic area, but also introduction to maybe what do you do with natural language processing? What can we do with computer vision in a very elementary way? So he said by the end of second year, he decided he's not going to work for any company ever. He'll be a researcher, lifelong researcher, and he continues that. He did a master's. He continued to do a MS by research here. He did a PhD in France. He is a faculty member in Germany now, and he's in touch with us, all of us. So this is the spirit of what research means. It's not about sitting in some dark room and hoping something will, some something will happen to you, some bulb will light in the head. It's a group, it's a teamwork. You work with your professor, of course, you work with your the members in the lab, and you learn from each other. In fact, it is very, very clear to all of us that the research students learn from each other much faster than they learn from the professors. So the idea of working in a team and building solutions in a team and keeping that keeping the benefit of doing this in mind always. This is what I want you to get a small sense of over the next this workshop. But also hope when you come here, some of you who come here for the internship, I hope you get to taste some of it. You get to see other students here, BTech, MS, PhD, all kinds of students doing the same. And I hope this, the bug bites you. We like to believe that, if you drink our mess water and mess food, you will get infected and you will become a researcher. You cannot do anything else. And that, like what happened to that student I mentioned. So this is what research is about. It is tough. I mean, it requires studies, it requires deep understanding, but it's all for a greater cause, greater satisfaction. So that's like Kiran Babu, that student said, I don't want to work for a company, I want to work for myself. That's the other thing in research. If you are a researcher, academic researcher, certainly you work for yourself. Even if you are a researcher in a company, you are building the next generation product. So you are at the top of the value chain. The company will depend on you rather than company saying, you do this, you do this. There may be broad direction, but it's up to you to channel the research activity. And of course, in companies, the difference is you would expect something to come out. I mean, they would expect something to come out, maybe a 6 month, 1 year, 2 year time frame. In academia, you want papers and students and learning to come out, maybe slightly longer. The product and impact may be slightly longer time frame. But it is, it's different. So company, you may have a little bit more pressure, or which is sometimes some people like it because you get to do things with some deadline. Some people think, like Kiran Babu I mentioned, I don't want to work for anybody. I will be my own boss. So this freedom and this being at the top of the game is what research training and research jobs gives you. And I think all of you, everybody, really wants to do that. It's the challenge is finding the right area, right passion, right problem. And steps to research, of course, is getting experience, getting a master's degree or a PhD degree. And but PhD degree is still just training. You're now fully trained once you have a PhD, but the race of research begins after that, when you are more and more in control and you are deciding your own agenda and you are building things. So that's the research life, that's the research journey that I want you to experience, introduce yourself to through. I mean, IIIT has been we call ourselves a research university. Our undergraduate program involves strong research component, and hence, the research is in the air all around here. And we want that excitement to be transmitted to much wider community, because we take only 200 students or 300 students in the undergraduate program, and we want to touch 2,000 students if possible. And online gives that opportunity. So that way, this kind of workshop being held online has another advantage. But I think combined, I welcome all of you to experience whatever happens in these days, understand, question people, note down things, explore all these yourself separately. Today with the internet, which was not so common until, internet probably was there 20 years ago, but there was very little stuff on internet at that point. Now you have all these opportunities. You note down things, you see what excites you, what interests you, you can learn yourself, you can write to us, or some of us here, like Deva said, contact some of us. If you have some questions or issues, come here when you are in the summer and work with somebody. And I'm sure you'll all choose a path of research after that. That's my hope, because you want to all make a big difference to the world. So I welcome you all once again to this workshop. Have fun, but keep your minds sharply tuned to what is being said, all the nuances, and think about it even after the session is over. It's not about just ending, listening to it and hoping that something will stick by itself. Make it happen. So once again, I welcome you and good luck to this event, and I'm looking forward to seeing many of you over summer as well as for the research programs here. Thank you.
Thank you, Professor PJ. So we'll take, there are any queries you can put out in the chat. Otherwise, we'll move ahead with our next speaker. So to introduce to you about research at undergraduate level, let me invite Professor C.V. Jawar. Professor C.V. Jawar is currently the Dean of Research and Development at IIIT. He is also the head of Center for Visual Information Technology and leads multiple research groups working on computer vision, machine learning, and multimedia systems. Professor C.V. Jawar graduated from University of Calicut in 1991 and later completed his master's and PhD from IIT Kharagpur.
I think we lost Dr. Raju. Okay, so I will continue. Yeah, so the quick introduction. I don't have the paper in front of me, but I think I know Professor Jawar reasonably well to introduce. So he's been a researcher in IIIT Hyderabad for the past 20 years, right? 20 years, 2002 to now, something like that. Yeah, so he's one of the most prolific authors and also a huge proponent of building products and innovation in research that makes a difference in the societal setup, right? So he has received a number of awards, and he has produced a large number of students who are researchers in universities, top companies like Google, Facebook, and you name it. His students are there. Right, so he is, one of the major awards that he received recently was the ACM. I don't remember the exact word, but I know the description. It's the ACM, teaching award. Right, so he's also known as an excellent teacher in computer science and computer vision, machine learning, and so on. Right, so he's a sought after teacher in many of these programs. If some of you are attending other, programs in IIIT, right. Skill development programs or Srishti later and so on. So you will get to hear from him more. I don't know how long he's going to talk today, but you'll hear more later also. Yeah, with that short introduction, impromptu introduction, let's welcome Professor Jawar.
Thank you. Thank you, Raju. Thank you, Deva. Thank you for inviting me to be here. This is an excellent opportunity for all of you to know IIIT, know the research, for all of us to know you and share what we know a little bit about research, whatever minimal experience that we have in research to share with you, etc. So, but I think before, and I hope I won't take much of time, we are possibly running slightly late, but still, I have a few points I thought I want to raise and discuss today. So feel free to unmute and speak or ask questions. Feel free to write messages in the chat. I think I'm also watching the chat, so I would like to see what you think. I think they are not just like people have logged in and went away. Like I want people to be live people in front of me. So the first question I have is, I have a set of questions. Like, why do you think undergraduate students should ever do research? So you're all mostly undergraduate students, whether you are an undergraduate student or not. Like, so there is a perception that you, or maybe you had many years back, maybe your parents had, maybe your teachers had, like, oh, just do well, get good marks, get a good degree. This is what generally the society advise. At least a large number of people advise this. Now we are thinking of doing something slightly different. When people are talking about research, which was considered to be a super narrow skill for a long time. Today, possibly it has been understood as a more important thing. Earlier, like a few years back, people could have told that, look, if I do a PhD, I get only a teaching job. Now today, people know that the PhD is becoming very, very important even to get a good industrial job or to earn money or to do business even. So given that, I think some of the perception that we had in the past had slowly disappeared. Now, my question is about like, why do you think undergraduate students in India should do research? Why don't you just focus on foundation? Nobody is saying kindergarten students should do research, isn't it? So there is a reason. Like, so now people are talking about undergraduate students should do research. Why? Okay, somebody says to explore the field and increase opportunities for further studies. Okay. Look, so you're seeing from your side. So my question is, why should an undergraduate student in India do research?
Probably because with the new generation, there are more new ideas that can be explored.
So you think that the new generation is better than the old generation, and that is what they should do? Not bad.
No, there's no comparison between generations, but just in general.
So I think that we have a little bit of understanding of how things are going to start molding, and undergraduate students have the ability to like get molded to newer perspectives and work on several other ideas, like have interdisciplinary ideas together, because we are flooded with ideas at this age.
Good, very good. Yeah, there's a comment about fresh minds can give new perspective. Beautiful. If the amount of skills we learn are doing research can receive from our normal curriculum, what is it? To develop our problem solving analytical skills. Okay, beautiful. Like there are a lot of, we can work towards our own future. Beautiful answers. Okay, it brings a new way of approaching problems in real life applications for gaining knowledge and explore new things. A lot of interesting. I think these are all valid ideas. Let me bring in a very practical issue and talk to you about. Assume we see a problem when we walk or when we move around in the society. How do we react? So you go somewhere and you see a long queue. You go somewhere, you see there is a traffic jam. And you go somewhere, you don't find enough appropriate people to meet your need or service or resources to meet the needs. Who is going to solve this problem? The problems that we face today in our own life and we complain about, who is going to solve? We should solve. Now, when I talk about we should solve, what I mean is, like, if you assume that this is something like a Microsoft will have to come with a solution and implement it here, or a multinational will have to come and implement here. They may do also. I'm not saying they will not do. There is money in it, and there is business in it. People may come from abroad and do that. Why are we not able to solve these problems ourselves? And many of these problems are perfectly in reach for you. So this is very, very important to realize. We think that these are things that I don't know, I don't have skills to solve. But you have clarity, you know the foundations required for solving the problem. They are being taught to you in your undergraduate studies or even in +2. You are not using it. So there is a big gap. So this is what I think we need to break today. The number of problems that we are facing today in our own life, starting from the power to resources to physical resources to whatever, the educational resources to many, many, many things that you can think of, that you are struggling and you are complaining about you, your family, your neighbors, your municipalities, your governments, your teachers, your college, like whatever you are complaining about, many of them, the solutions are with you. You may say, now, how do I change the world? That comes next. I'll tell you how do you change the world. That is possible to do. But let me take a working example and talk about this issue. So you say that, okay, I want to travel from point A to point B, and there is a traffic jam I see on the way. Now, how do I ever solve this problem? Because you are driving a bike or a car or a bus or whatever it is you are riding, and then you realize that there's a traffic jam and you are complaining about, like you can say, no, let others all not travel. I will travel, that there is no traffic jam. That is not the solution that we want. Or you say, no, let us widen the road. Oh, it requires a lot of investment from government. It is not easy for government to invest possibly that much of crores or rupee to widen the road. So how do we fix this problem? So if I give you this as a question in your final exam, how will you solve it? I'm not even talking about how do you go and practice it first. So first issue is about, will you be able to solve this problem in your mind? How will you solve?
By arranging for someone to systematically guide people about when you can go, when you cannot go, like traffic police does.
Good. So did you use anything that you studied? No.
Not really.
No, you did. It's okay. So it's okay. So you have been taught this heavily in your college, in your curriculum heavily. You are not still using it. I'll tell you what is the story. The story is very simple today. You know graph. You look at the road network as a graph, and if you want to do travel from A to B, what is the simplest way you will plan? You will route through different paths, isn't it? There are many paths from A to B. And today, when I want to travel from A to B, I know only one route, the main road or whatever it is you call. And then I travel through that, and everybody travels through that. I know one route, you also know one route, and both of us are traveling in the same route, and there's a traffic jam.
Yes.
And if I had known the second route or an alternate path, which could have possibly taken 1 kilometer extra, I should have taken that and reached in the shortest time. And that is possible if I know graph and how do you navigate in a graph navigation, graph traversal, paths in graph. There are many things that you might have studied, isn't it? Many of you, this might have taught you in the first year of undergraduate curriculum. And you thought that this is only for scoring in exam. This is where everything went wrong. So you are not using what you have learned in the right form. And now let me ask a next question. So whoever practiced this, Google Map practiced this, isn't it? See, in the Google Maps, when you use today, I know that you're all going through the main route, and Google Maps tells me take this route so that you will reach faster than your friends. And it increased the effective utilization of the road network extensively. When you travel today, you go through new roads which you never thought existed itself, and you're reaching destinations much faster than what you could have gone in the main route. And what in the back end is the type of algorithm that you have studied in your data structure course itself. So I can show you a number of algorithms. Yes, there are many algorithms which will be useful in such situations. And of course, so the question is now, if I ask you this question in an exam in your course, or in a viva in your curriculum, or somewhere in the third year, fourth year, somewhere, are you ready to give an answer based on what you know? This is very, very important today. So you think that what you study is one way, and what you need to practice is something else. Sorry, it is not. This, if somebody else has given this message to you that, okay, no, what you study is all useless. At the end of the day, what you need to know is only Python or Java, then you are going to make your earning. Sorry, you're wrong. You may get your the bread and butter for the first year, or you will make your living for the first few years. But this Java will be replaced by a Python, and Python will be replaced by some other beast tomorrow. So what you need to know is fundamentals. And as an undergraduate student, you are taught heavily the fundamentals. And when the fundamentals come, you close your eyes and say, these are useless things. Why are you teaching me theory of computation? Why are you teaching me these courses? These are completely useless courses. I don't want to even attend it. I don't want to take it seriously. So you have to emphasize on the fundamentals. understand the concepts well, see how it is related, think about it, what is its implication, and use it in the right place. And that is what is research as a starting point for you. So, to solve many tough problems of today that we are all facing, you know the foundations, but you may not be capable of, like I said, thinking out of the box suddenly. And you may need a feedback. So this is where you need a mentor. Your mentor generally, like in research, people say it is very important to have a mentor or a guide or an advisor or whatever you may call. Why? Because that is where you get a system, say you get feedback on how, like, is this thinking right or wrong, or what is the next step? How do you do that? So you can do a lot yourself. For example, like as I mentioned, like a solve problem that you are facing every day in your own way. If you write the traffic jam avoiding is a graph traversal problem, that is a first level answer. I'm not saying that that is the end answer. There are a lot of things to be done on top of it to reach where we are today. You get a glimpse of what to do, and then you go and read some literature. You search online, you find some papers, you find some books, you find some blogs, you find some videos, you go through that, you get some more ideas, then you see, can I implement it on some toy example, some networks, and see what can I do. Then suddenly you realize, oh, this all graph, all the social networking is all graph. People say, what is this there? So then you find some other interesting problems. So you jump from one problem to another and solve problems that are socially or technically important at a young age. Some people continue to enjoy problem solving. They enjoy the thinking process. They enjoy the lifestyle. For example, the thrill of, like I can see when I explained you that it's a graph, like many of you, oh, I never thought that way. And that gives you an experience, a trigger in your mind that possibly lasted only for a few seconds or not more than that. You want to be in that mental state forever, excited state of enjoyment, which come from thinking, which come from solving practical problems, which come from solving problems that matter to everybody around us, that come from the enjoyment of solving problems and becoming billionaires, or that comes from the solving problems and creating jobs. So you may have different viewpoint for your career, but it all gets rooted from that thinking. So you need to. So this is what as an opportunity that you have in front of you as an undergraduate students, and you should surely jump in and take the risk of enjoying and going to a new phase where you are not just a simple job seeker. If you think that as an undergraduate student, my worry is about where will I get placed, when will I get placed, what will be my salary, you have to correct yourself. So as a researcher, we want people to be confident that they are not running for jobs or they are not worried about jobs because they know what is really required to do. And it is not all about getting this earning in this month, isn't it? So by this year 2024, by this month I need to have a job, and say, look, you have a long career for you. You are very young, and you don't have to worry. You check with your parents or friends or say senior cousins, when did they start working for a job? It is not at very young age. So it's okay, perfectly okay for you to wait for a few years, say enjoy the life, enjoy the learnings, practice it, and then decide where to go. By that, your value also increases. And when your value increases, you naturally start to work with better jobs or better opportunities, better places, better organizations, better friends, better colleagues, and that will take you to the next orbit. You don't want to think of taking up something which is immediate and somehow get a job and somehow get an earning and then look for how do I jump to the next job. This is not going to take you where you want to be. You need to improve your value. You need to know more than your textbooks. You need to solve the problems at the end of the textbook, but you also need to know solve real world problems, solve problems beyond the textbooks using what you have studied. And that is what generally you start to see when you do internships. And remember, these are all commitments which are for long. If you think that, okay, look, in 3 months, how many such problems what can I solve? How many such startups I can do? Sorry, this is not going to happen. You have to be patient. You have to work on, say, if you want to do, for example, do a good idea, good startup, good, bigger impact, you have to invest a reasonably long period on that. So internships will have to be thought that way, rather than thinking that I will do 10 internships and this is one more of them. It is not going to help you. Whatever you do it seriously, go deep, and you are going to get benefited by that. Okay, so plan for such a research career. When I use the research in a very broad sense, the examples I gave you, and contribute to the country, contribute to the family, contribute to yourself in your own growth. Thank you. So welcome to this program.
Thank you, Professor Jawar. So that brings us to the end of this inaugural session. Thank you, Professor Deva, Professor PJ Narayan, and Professor CV Jawar. And for all the students, you have already been invited to IIIT Hyderabad by these professors. Professor Deva has also invited you to visit iHub. So that's a big round of applause for all three of them. And now let us move on to the technical sessions that we have planned for you. The session coming up is a talk by Dr. Subhadeep Mitra of CCNSB, and he would be talking on At the Edge of Science. Dr. Subhadeep Mitra completed his graduation in physics from University of Calcutta in 2001. He did his master's and PhD from IIT Kanpur in 2003 and 2008 respectively. His postdoctoral fellowships had been from Institute of Mathematical Sciences, Chennai, Institute of Physics, Bhubaneswar, and Laboratory of Physics Theory in France. He had a brief tenure as a senior project scientist at IIT Kanpur, and since 2015, Dr. Subhadeep is with IIITH as a member of faculty in Center of Computational Natural Sciences and Bioinformatics. His broad research areas are in high energy physics. So let's hear what Dr. Subhadeep Mitra has got today. Over to you, Dr. Subhadeep.
Okay, thank you very much for giving me this opportunity to talk with these young people. From what I understood from Dr. Raju's mail, that I have to talk about the splendors of science. Now, okay, how do I share? I need to share my screen. So can I? Okay.
Sir, you are muted, sir.
Hello, can you hear me?
Yes, sir. Yeah.
Right. Okay, just give me 1 second. Yeah. Now, the age of science is a difficult question, because you can, science is all around. I mean, it's investigating in every possible directions. For example, so we can, if you have read Hitchhiker's Guide to the Galaxy, so you know that Douglas Adams says that, okay, there are 3 basic kind of questions that you need to know. For example, you need to know about life, and then you need to know about universe, and whatever rest is everything. Okay. So I think that we can start from there. So, for example, the ages of science, one can think of this tardigrades, okay, that can that is the tiniest of creature that can withstand extreme heat, interstellar distances from this big blue whale. So one can talk about the ages in this direction. So about life, or if you want, you can talk about the universe as well. For example, so this is, I show a recent picture of Neptune that the Voyager 2 has taken. It's actually a very recent image that has passed through that has recently gone out of the solar system completely. Or you can talk about the entire universe. For example, here I show that this is.
Pardon my interruption. Your screen is not visible. You'll have to share that again.
Okay. But I shared screen on it. Okay. I'm very sorry.
Yes, screen is visible now, Dr. Singh.
So you're not audible.
Hello, is it visible now?
Yes,
Yes.
visible.
Visible and audible.
Okay. Sorry for the. Okay. So, Dr. Raju, please alert me whenever I'm close to my limit. Okay, give me a ring, say 5 minutes before.
Sure, sure.
Okay, great. So we can talk about the universe. For example, here I show that. Okay, so this is the Hubble Space Telescope, and this is this James Webb, the recent telescope that went up, and now it's taking pictures. So, and it can probe. So, as we know, as we look at the sky, we are basically looking at our history, the past history of universe. So, this is because universe started from a very small dot, and everything started in the Big Bang, and it kept on expanding and expanding. Okay. So, and those lights from the very early universe are just reaching us now. So, as we look further and further, we are actually seeing back and back at the history. Okay. So, this is, for example, the range of Hubble's, and now in 2022 we sent out this James Webb telescope, and this can probe here. Okay, but we are still far away from the beginning of the universe. So this is another age. Okay, or for example, this is a recent photograph taken by this James Webb telescope. This shows pillars of creation. So this is Eagle's Nebula, and this image was taken by Hubble. In the image on the left was taken by Hubble in 2014, and now with this advanced technology, it has more cameras, more multi-band cameras on it, and so you can merge this image, and of course you process through computers and create this beautiful image of our galaxy. This is part of our own galaxy. So this is Eagle's Nebula in a corner, in an opposite corner of our Milky Way galaxy. Okay, so you could actually go to the edges of science in many ways, because as Carl Sagan says, we are standing on the shores of cosmic universe, and the shore is all around us. So the edges are in every direction. Okay? But I can only tell you about what I know better. So today I'll just take you through a arc. So not all the edges, but only a thread in the one direction. Okay, where I work in, or some people, other people in AAA to work on. So I'll just tell you about that, and let's see how it can come across. Okay. So now I have talked about the life, from the smallest tardigrades to play with the great blue whales. I've talked about the universe, and now this company, whatever, this web dev studios, have figured out how to know everything. Okay, so that's great. I mean, so basically, according to Douglas Adams, we practically know everything, because these are the three kinds of knowledge that we do. But wait, so is it really everything? It turns out that, I mean, of course, in that philosophical sense, Newton said that we are just picking up pebbles from the in terms of knowledge. But I'm not talking about in that philosophical sense. It turns out that there is a great darkness all around. Okay, so maybe it's a universe like this Lord of the Rings or something. Okay, there is a dark Lord, and we know nothing about. It turns out that in science also there is a dark Lord. Okay, it's actually called. It's not one dark Lord, but two dark Lords. Okay, there is huge part of the universe which is called dark energy and dark matter, which we know nothing about. It turns out that all that we see, all that images, that beautiful images that I showed you, comes from this tiny part of this universe. So this is a pie chart of the entire universe. So the entire mass energy budget of universe. So it turns out the almost 75% of the universe is something called dark energy. It's a form of energy that actually has a negative pressure that forces the universe to expand. And it's called dark because it does not interact. It has no connection. Only effect we see is through gravity. So it actually forces the universe to expand. That's the only thing we know. We have no clue about its nature and what it does, what else is done. And then there is dark matter. We know that there is some mass, okay, because we can see the distribution of the galaxies, and from there, using simple Newton's law and maybe with correction of relativity, we can calculate that how this mass should be distributed with respect to their velocities and stuff. And we see that there is a mass imbalance, and that mass is called dark matter. And clearly, we won't see the mass, so that means it does not interact with electromagnetic. And it turns out it does not interact with anything at all except gravity. So basically, it's the entire universe is dark, not in the just philosophical sense, but in true sense, scientifically also. It's everything about dark things, okay? And what we know is only about this tiny part. So all of us, whatever the visible universe is made of, is basically in this green small part, and this yellow part, this tiny yellow line is all lights that we see around. Okay? And then there is a type of particles called neutrinos, host-like particles. They hardly interact with anything, and they are all going through our bodies. At the moment, I mean, right now I am talking with you, and billions of neutrinos are passing through my body, your body, everyone's body. Okay, they're passing through Earth, everywhere. They are all around us, and they are almost massless. We don't see them, and they don't interact, so they don't harm us. They don't do anything, but we know that they are there. So this is all we know. Okay, but even in this small thing, so what do we know actually? So it turns out that we know not a little actually. There is a lot of things to know about. For example, earlier people thought that okay, all that we see, that means the visible part of whatever we see around us, are made up of these four elements, okay, air, earth, fire, space. But from there, when after the discovery of microscope, etc., we know that okay, this is not a full correct description, so you cannot formulate everything in that manner. So we know that now, okay, we are made up of small, tiny scales, the cells basically, and then these cells are made up of tiny, I mean, if you go smaller and smaller in scales, then you will hit here with molecules, okay? So up to here, you can kind of see because you have electron microscope and stuff. And this is this is how you enter the domain of chemistry. So here you have the periodic table, and with this level of idea, you can explain the periodic table and stuff. But we know now that okay, this is not the entire picture because the molecules themselves are made of atoms, and then atom has electrons orbiting about the nucleus, and the nucleus is made up of proton and neutron. And now we have even discovered further that okay, this is even proton neutrons are not elementary particles, but they are made up of something called quarks. Okay? So right now, as we understand, the quarks and the electrons, they are the true elementary particles. But this picture could change any day. Okay, so we might discover even finer structure. Even we realize that okay, even these particles are actually composite particles made up of something even more fundamental that can happen. But as we know currently, this is the structure that. And now, with all this knowledge, so initially we had this periodic table where we have a lot of elements, but once we find that okay, there is a way to arrange them, then we understand that okay, to remember the structure, underlying structure, you don't actually have to remember a lot of things. You just need to understand the organizational principles. So basically, you have to find out the laws, okay, how they are connected. And so when you go even smaller and smaller,
Shubhadeep, your audio I don't know if it's just me though.
On that scale, it turns out the law is need to know. I mean, whatever we know about all, is it? Or am I audible now? Look.
No, it's okay. No, it's okay.
Okay. So I don't know what is happening. I'm just losing audio. I'm connecting through Chrome. Probably that could be one reason. All right. So it turns out that we don't need a lot of things to remember. So you see this mathematical equation. This basically describes all that we know about the particle, contains all elementary particles, and this is called the standard model. Okay. So of course you need to know the meaning of this notation, but they are not too difficult to understand and not too difficult to remember. Okay. So now we know a lot better, and we have found a very simple underlying principle. Basically, using some symmetries. That symmetries means you do something and nothing changes. Using this principle, you can actually explain practically all the visible universe. And this standard model is remarkable. Remarkable in the sense that using it, you can predict things. Okay, you can calculate things. For example, here this I show a number. This is taken from a very recent paper. Okay, it's called the fine structure constant. It's basically the square of the charge of the electron. Okay, and it's measuring the charge at 10⁻⁻10 level accuracy. So that's just to give you an idea. Suppose somebody tells you, I know the distance from Earth to the Sun, or the average distance from Earth to the Sun, to the level of 20 meters. Okay, so that much. So that means I know that distance up to that accuracy. So it is that. Or suppose somebody tells you that, okay, I know the length of a football stadium up to the width of a grass, single grass. Okay, so it's at that level precise. So we know it very well. Even that simple equation, it explains things very well. And now this is the description that, okay, so earlier that this is the structure of the atom right now that as we understand. So this is the electron cloud, and inside these there are protons and neutrons, and protons and neutrons are made of these quarks, and there are different types of quarks. And in fact, we have realized that there are different types of electrons as well. And for every different types of electron, there is a corresponding neutrino and so on. So we all know the particle content. There are 6 types of quarks: up and down, charm strings, top, bottom. So they have slightly different properties, but they are similar. And it turns out that even the interaction that, for example, in classical mechanics, we see that we learn Newton's force law, F equal to ma, right? That force is actually in the when you go to these elementary particles, this force is even carried by some particles. Okay, so even force is a realization of particles. So when I see you, we are actually exchanging photons. So similarly, there are other types of photon inside the nucleus. Instead of photons, something like called a gluon is exchanged. Okay, so this gluon, it comes because it binds the nucleus tightly, so it's like glue, hence it's called gluon. Okay, so this is all known, and the last puzzle that was missing till, before 2012, it was discovered. You might have heard about it. This is the famous announcement of Higgs Discovery, and this was the current director of CERN. And because of that discovery, these 2 gentlemen, Peter Higgs and Francois Englert, got the Nobel Prizes for that. So right now we can say, great. So we know all about there to know about our visible universe, the elementary particles we have, so starting from this ancients, so where they thought about this Paramanu and Anu and whatever, we have come to this. So this picture actually shows that all that we know about particle physics, and they publish every year. They publish a review book, and this starting from this very thin book, and now it is this fat. Okay, so we have learned a lot, and everything comes from that simple equation that I just showed you. Okay, and so with some measurements, we can actually basically describe everything around us. However, it turns out not fully, but because there are some challenges that we still don't understand. Okay, so I don't want to go into that because that requires certain technicality, because we don't understand why we see things around us like that. For example, why things are so light, some things are so light and some things are very heavy. So that we don't understand. And why the Higgs that was discovered has certain mass, that we don't understand. So there are other theories. So other theories that says that, look, the standard model is not the entire picture. You need to augment it with some bigger theory. So just like Newton's gravity was a part of Einstein's theory of relativity, the general theory of relativity. So you can, in one limit, when the speed goes to very slow. So Einstein's gravity and Newton's gravity are the same thing, exactly similar manner. So it is possible that if you have higher and higher energy, the energy, why? Because see, to probe smaller and smaller things, the uncertainty principle in quantum mechanics says that you need more and more energy because the space and momentum are inversely proportional. So you need more and more higher and higher momentum, which translates to more and more energy to probe smaller and smaller things. So if these things we are not aware about, so they must be very, very tiny. That's why you have not seen. So there are different proposals. For example, one is called supersymmetry, another is called extra dimension model. So this is fantastic. It feels just like science fiction that I mean, we might be living in not a 4-dimensional universe, but a fifth or even higher dimensional universe. So you can have all these theories, okay, and they are there. So these are all scientific theories that people propose, and they are looking for this how to test ways to test these theories in different experiments. And this is what I'm coming to next. So the thing is now, okay, you can have your favorite theory. You can say that, look, I have a theory that can explain better than the standard model, because there are many such theories, but we need to test them. Now, where to test them? Because we need to create a lot of energy to probe the theories which talks about things which are even tinier than the quarks or whatever we see, whatever is described by this standard model. So what we do is basically we accelerate particles, okay, accelerate particles and give them enough energy, and then very high energy, and then let them collide. So since we know that from Einstein's relativity that energy can be converted into mass, the idea is if you create enough high energy collisions, so those energy will be converted to some form of mass. Maybe these very tiny particles will also be created, and then you have to detect them. So this Large Hadron Collider works on precisely on this idea. So this, which we call as LHC. So this is a huge, the image that you see is the France-Switzerland border, and it goes underground. The perimeter is 80 kilometers long, okay? So this is where you accelerate protons. So 2 beams of protons, one in moving in this direction and other. So one is cyclic, another is anti-cyclic, and there are 4 crossover points, and these crossover points you have 4 detectors. Okay? These CMS, Atlas, Alice, and LHCb, and where these almost there, these protons are accelerated almost close to the speed of light, 0.9999 of speed of light, and then we collide them. So they create huge energy, and we try to detect them. So this just to give an idea. So inside, deep down, like 1 kilometer down, you have this big of this is the Atlas detector. Sorry, this is a CMS detector of. I mean, this part actually India developed. Okay, it was developed in half of it was developed in TIFR Mumbai, and half is what developed in this VECC Kolkata. Part of it, I mean, not the full detector, some detector mechanism was developed in India. That's why I show this particular figure. And just to give you an idea that, okay, this is the scale. So this is someone is standing, and this is this huge, and this tunnel is that big. Okay, so these are the lines through which the protons travels, and here they collide and you detect. So this detector is open, and then you connect to this tunnel. Now the question is, what happens inside that? What exactly? How do you see them? Okay, I have a big collider, and I have some theories. How do we connect it? And this is where the our role comes. Okay, so What happens inside is a tale of wonderful technology and wonderful computation. Okay, so you collide the proton beams, and protons, the quarks out of those protons come out, and they hit each other. And as we predict, so they create a lot of free energy which are converted into particles. Okay. For example, here I show this figure is taken from one Atlas collision. Okay, so two proton beams. This yellow line is a proton beam line, and there is another here on the left side that's not visible. They have collided, and these jet-like structures are just showers of particles. So every collision can create like hundreds to thousands of particles. So all these lines, that the red lines and this blue lines and this cone-like structure, they are just a bunch of particles. Okay. Now the task is challenging because these collisions happens over femtosecond order, and you have to identify them. You have to know what are these tracks. Okay, so the detector is quite complicated. For example, we can know the energy deposition, we can know if they are charged or not. We can know that if they are charged, if say for example two particles are equally charged or oppositely charged, so using some magnetic field, you can see that how they are bending and stuff. But if something is very fast, then they can go out immediately and we may not catch them. For example, if there are neutrinos produced, we will not see them. So the detector can detect some jets which are like quarks coming out of these collisions, electrons, muons, which muon is like a heavier copy of electron, and all this happens less than a femtosecond order. Okay, and we have to track them. So that's challenge. And so similar thing, this actually part of that. I mean, after the Higgs discovery, they were probing the Higgs channel more, and so this is one of the collision, real collision event. Okay, so the detector is this tube is the LHC tube. So this is where the beams are crossing. One proton is coming from the left, another proton is coming from the right, and they collide. And this is on fully surround. The detector is placed surrounding that collision point. So this light green shadow that you see is the detector, and on the detector how these particles emerge. So the red and blue are different energy deposition, and the greens are the extra particles that come out, and we have to identify them. Okay, so you see that this is a huge computing challenge, but the identifying the particles is just one step, and we have to connect it with the theory. So whatever so suppose you say that I have a theory which tells me which works better than the standard model, so I have to test it. Now you need to way to figure out how to test it. So what you have to do is basically say that, okay, if I collide two protons, how is your theory behaving differently than standard model? And obviously, because all what your theory is predicting extra than the standard model is very small particles. So only in very rare cases, because these will be high energy heavy particles or tiny particles, and you need to produce them. To produce heavy particles, you need more energy. So only in rare cases we will be producing them, and those exceptionally rare possibilities have to be identified. So you have to calculate and tell the experimentalists, look, that if you say run the LHC for like 20 years, you should see this and this kind of distribution, or this and this kind of special property in like say 200 times, something like that. So here I show the diagram. This is a representative diagram. These diagrams are called Feynman diagrams. I'll tell you how to understand this. For example, here we show that, okay, one proton, these are the two protons, colliding protons, and two gluons are coming out of these protons, and whatever extra is there inside the proton, they just pass through one another. So two gluons are carrying the energy from the protons, and they connect and create this H naught is the Higgs particle. Okay, so they create Higgs particle, and then the Higgs decays to heavy photon-like particle called W, whatever that is. So they are something like a massive photon and then this W decays to one positron, which is an antiparticle of electron, and this W minus decays to electron, and these new are called neutrinos. Okay, so you produce one electron, one positron, and two neutrinos. Obviously, these two neutrinos you will not be able to see because they will immediately cross through the Earth and escape in the universe. But these electrons, since they are charged particle, you will see them. Okay, so now you have to look at the distribution of the electron and see if there is a tiny departure from if this process were not there. So this is the challenge. The way we understand this gluon or these particles is, I mean, this diagram actually shows. For example, you can understand this how these forces can come through particle exchange. Just imagine two guys are throwing football to each other. Okay, so you immediately realize that this way we can actually mimic a force applied on each other. And if this guy is throwing the ball not to this guy but just in front, so this guy will, the guy on the right will come a little forward to catch that ball. Okay, so we can model both attraction and repulsion this way. It turns out this is how it happens, and that's why we see this. So basically the gluon is nothing but a football that is coming out of this football means I mean this ball that comes out of this proton, and this gluons are then creating a new particle. So this is this diagram now. But the problem is, unfortunately, the image is not very clean. So whatever happens, whatever we calculate, I mean, this we know from how to calculate from quantum field theory, and I can tell you the rate and stuff, but calculating the distribution of the final particle is not easy at all. The reason is very simple. So here I show the same problem, but from a different angle. So here you see this, these are the two protons. Okay, so these are actually giving the gluons, and this is this diagram is represented by this red blob. But and they are giving out the final particles and they are decaying. But this is not the only thing that is happening around, because these are highly radiative, highly energetic particles. They radiate a lot of other associated particles. Okay, so the entire thing is a mess, because we are only interested in this part, but because these are high energetic particles, they create radiation, and everything is overshadowed by this radiation. And there are multiple steps and multiple physics involved. But one good thing that saves us, actually, we can analyze from this mess. We can separate out the actual process, because the actual process, which happens at a very high energy, happens very fast. All these unnecessary extra details that happen slow. Now, when I say slow, I mean that it's still in femto1, but a slightly lower value. Okay, but this separation of time scale allows us to guess something that, okay, this could have been the actual underlying process that has gone through. So this is that. Here comes the role of computation. So basically what you do, so if you have a theory, so you can say that, look, I have a theory that works better for standard model, blah blah, and that. So now you give this theory to computer simulators, so which can actually mimic the LHC environment and say that, okay, if you have this kind of theory and with such and such properties, then I can tell you that this is how the ultimate distribution is going to be. So all these simulators and everything are publicly available. So anybody, if you know about it, you can actually generate. For example, the Higgs process that I showed you, we can immediately create it, and this entire package is available freely online for everybody to use. Okay, so you can actually create a simulation of this kind of process, and you can see yourself that, okay, this is how the process will differ from only the standard model prediction. So from the difference, you have to understand that, okay, now we have this. So there is a departures from the standard model or not. So if there is something extra, hence we call the new physics. So if there is some new physics, no. So that's the challenge. And here I just show you some ones, just workflow of this how this simulation will work. Okay, so this is basically when I have quantum field theory, I can calculate the probabilities, and when I have probability, I can do Monte Carlo generation based on this probability. So I can generate events, that means false scattering, mimic scattering, depending on the probability that I get from quantum field theory, and then I can mimic whatever is this radiation. These are called Parton showers and hadronization, and I have a simulation for these detectors, the Atlas and CMS detector that I showed. They are also public, so I can run through those public detector simulation and say that okay, this is how you will see the difference or not. So this is what we need to tell the experimentalists so that they can actually do the experiment. For example, this is one taken from one paper that we wrote. So this is basically a publication, one of our publication taken from there. So here in this process, what we are looking at is the creation of two heavy B, the quarks called B for some reason. Okay, I mean the name has some meaning, but we don't care about that. So it basically talks about creation of two heavy quarks that you normally don't see, and which decays a particle called phi, another light B quark, and another wing, it decays to a top quark and a W boson. So whatever, some details. So this is the typical structure. Now, just to give you some idea, the challenges involved. So now our task is that what standard model processes can also give similar signatures. So basically, I need to look for events which has a phi, B, T, and W. So now we ask, can other standard model things look the same? Because we need to identify events with these properties. It turns out that yes, they are, and not only they're huge. For example, if this theory is true, if these B particles exist heavier than the standard model particles, then the probability of creating them is like 10 to the power 8 down than the leading standard model particles. So that means out of every 10 to the power 8 events happening, only one might be coming from the true signal. Okay, so it's an incredibly rare process. So it's far more complicated than finding it, in true sense, finding a needle in a haystack. But it can be done using. This is again taken from our result, and here we have used some machine learning technique. Even though we cannot, the machine can actually sense through the distribution. Okay, so the task, once you define know this probability distribution, the task that you do is actually very standard. So you have a signal and you have a background. The background is huge, so a haystack, and you have to find the signal which is like a needle, but it can be done. And here I show that okay. So for example, some parameter space you can have a 5 sigma confidence level, which is like 0.99999 fraction or 99.999% certain that this kind of particle exists. And here your confidence is slightly less. It's 97% certainty you can say that this kind of particle exists, and beyond that you are not certain that whether it's coming from this particle or the standard model. So this is a prediction that the experimentalists will take over, and then maybe after once the LHC, I mean it's currently running. So once they collect the data for 15 or 20 years, they will analyze it and say that we have found it, or say that no, we have not found it. So that way we can say that this theory is either wrong or right. So this is a huge task, and the challenge is marvelous. Okay, I mean fantastic. The scope is huge, and they have a huge. I mean we work in a huge collaboration. So all the high energy experimentalists have put their strengths together to form this collaboration. So these collaborations are also named after the detectors. So for example, this Atlas and CMS detectors, all of them have more than 5,000 active scientists, plus students, postdocs, and a lot of engineers. All of them collaborate. So this is a earth-wide collaboration. So that means Atlas and CMS, although physically they are in CERN, Geneva, but basically the France and Switzerland border, under the France and Switzerland border, but the Atlas and CMS people are all around. For example, India is part of the CMS. CMS stands for Compact Muon Solenoid. So it's a huge collaboration. So if you just open up archive and open one paper from CMS, you will see the names of 5,000 people who have contributed to one particular experiment. And that's the practice, because things at this scale, it's impossible to achieve otherwise unless you have a solid collaboration. And obviously, this is a technological marvel because nowhere. So this is not only the age of science, it's also age of technology in one particular direction. Nowhere you will need this level of precision, this level of fast equipment. So everything happening in nanosecond, femtosecond, not nanosecond actually, is much smaller than nanosecond. So basically femtosecond order, and you need to capture that. So for that you need triggers. So that means something happens and the computer starts recording. So that trigger has to be that precise, that fast. Okay. So there is no other place on earth where you need such things. And the good thing is that, or the wonderful thing is that we have been successful. So in fact, just to tell you, we today have World Wide Web, right? What we call as internet. Okay, this internet was born out of CERN for such an international collaborations to share the huge amount of data fast with the people all around. That means some people are sitting in USA, some in Europe, some in Asia. So to share, the idea of the current wave was born there. Okay? And so, but okay, so collaboration is good, but the thing is that you clearly you have a huge scope of computing, advanced computation. So you not only need good instruments, superior instruments, manpower, but you need really, really efficient strategies. Otherwise, you are going to waste a lot of resources, because as I just showed you, right, out of 10 to the power 8 events, okay, so that means out of 10 crore events, only one is signal. And if you miss that signal, then you have to again wait for next 10 crore events. Okay, so it's that, and this signal is actually one of the hopeful signals. There are even more challenging signals than this. So I just took an example which is slightly easier to do, but there are even more challenging cases. And if we want to test theories beyond standard model, we have to test these. Okay. So we need efficient strategies and algorithms. For example, there are many directions people are working, and as I said, this is a worldwide collaboration. So they are here. This is the Quantum at CERN webpage. So they talk about the possibility of using near-term quantum computers. Okay, so this is another direction that IIIT people are working on. I did not talk about it today because I have only limited time and I chose only one thread. So how we can use the current quantum computers. So quantum computers, we know that are not yet fully developed, right? So, but in near term, we see that we will be somewhere to compute some basic things. Now the challenge is that, can we use this near-term quantum computers to make meaningful computation? So so it's a hybrid computation. So part of it is classical, where it can handle a lot of things that requires powers, but where we need real boost for so parallelization, or we want to probe the quantum nature of the interactions. Can quantum computer play any role? It turns out it can play a huge role. So CERN is actually has a fully formed working group on quantum computers. So if you are interested in that, so you can easily contribute there. So this is to give you how big the challenge, show you how big the challenge is in near next 10-20 years. So this this figure I took from one blogger in computer science. So he blogs about interesting stuff in data science. So he plotted the available data, whatever data was available in 2021 based on that. So here it shows that, okay, this is the size of the Amazon Web storage. So this is the amount of data we are talking about when we talk about AWS, and this is like Google. This is YouTube. Hello. Any question? Sorry, I cannot see the screen. And compared to that, you see this gray corner. So this is the data, the raw data, the raw collision data that LHC produced in 2018 alone. Of course, this data is not useful because most of them are just known standard model thing. So once you clean them, so that you just select the probably serious candidate, probably signal like. So you pass through the pre-levels scanning and you come out here. Okay. So this is the real data. So from data of this size, you filter it to this size. Okay. And this is about to grow 10 by a factor of 10 each coming year. Okay. So LHC is already running. So it's collecting 240 petabyte per year data, and so clean data. So, but the raw data is huge. So when we talk about big data, so just remember that the biggest data set on Earth is actually coming from the LHC, and so they have created this worldwide LHC grid computing. So this is a grid computation. The grids is throughout the world. As you can see that they have 170 computing centers in 40 countries. Okay, so this because clearly they cannot do it alone. But this grid computing they're talking about is this level data. This pre-processing they do it alone, but with the raw data. Okay? And then this clean data. Clean means clean by one step. Is then distributed through this grid and then analyzed for next. I mean, it will take a lot of time to analyze this data, and then we can talk about this the physics goals. Okay. Now, one thing I just wanted to, before I finish, I wanted to tell you that, okay, so this is all fine. So you might wonder, good, I know that, okay, you need to know quantum field theory and a lot of things to do, and if you know that, you can see some wonderful things. Good, but what do we come in? Okay. Now it turns out that that's not the case. So you need a little bit of knowledge of programming, and then CERN is open for you. So every year CERN opens up their summer projects and challenges for kids. I mean, it need not be kid, it can be anybody, to help them with coming up with better and better algorithms. So here I just show you this. I have taken from this their website. Okay, so this is this year's summer code. So this is GSUP page hosted by with the CERN program. So here they will tell you, okay, forget about the physics goal. I'll tell you about the this is the nature of the problem, that I have some particles with such and such momentum. So basically particles are represented by their momentum and energy. So basically a collection of numbers. So the data is form of a table. So from that table you have to design algorithm which can identify particles of such and such properties. So this is basically the entire scheme. And for I mean, of course, students are these students can be a lot of them are actually coming from this school. Some of them, even our students have taken part of this in the CERN summer program. So there are different possibilities that where you can contribute. See here that the working groups are data analysis, detector simulation, frameworks, and so on. So it's not true that you need to know a lot of physics to join in this program. You can do it if you know some programming, and if you understand how to handle a lot of data efficiently, or if you think you want up to a challenge, you're welcome. This is open for public. And not only that, so this I told you only about the LHC, but LHC is not the only detector currently running. So there is another detector deep in the South Pole. Okay, it's called ice cube. So it's so just to show you, this is the American base, this Amundsen Scott station. So underlying that base, you have a detectors to detect this neutrinos. Okay, neutrinos that I told you that billions of them are passing through our body because they are almost massless. They don't interact. So the newspaper calls them ghost particles. So detecting them is very, very challenging because they interact so feebly, and if in presence of background, everything can be spoiled. So they have installed the detectors inside the ice of South Pole, deep inside, and they have posted this competition is actually online now. You can join in if you want today, if you understand the thing, and they have declared a huge money, okay, prize money. So whoever can come up. So here the goal is, so they want to identify, increase the resolution of the tracks. So there are two tracks, and they are almost merging on each other. So the challenge is whoever can identify these two tracks, separate out these two tracks with the maximum angular, the best, will probably win. That group will probably get the money. And probably, I say probably because I don't know whether this is only for one group or they have first, second, third. That I don't know. So that's why I say probably. So with this, I think I'm kind of done. If you have any question, feel free to ask me.
Thank you, Dr. Subhadeep. It was nice. In fact, you took us to the edges of science at both at the macro level to dark energy and at the most fundamental level in particle physics. So thanks. At least the edge of you've given a different meaning to the terminology of edge. And I guess the interns will be meeting you when they are here in the campus. Thank you, Dr. Subhadeep. Now let's move on to the next speaker. Professor Kishore Kottapalli is the Dean of Academics at IIIT. He did his BTech in Computer Science from NIT Warangal and MTech from IIT Kanpur. His PhD was from Johns Hopkins University, USA. And from 2006 onwards, Professor Kishore has been with the IIIT Hyderabad at CSTAR, the Center for Security Theory and Algorithmic Research. And his research areas are in distributed and parallel architectures and algorithms. And today, Professor Kishore will be talking to us on algorithmic engineering. Over to you, Professor Kishore.
Okay, thank you. Thank you, Raju. So let me just share my screen and then we'll get started.
It's visible, Professor Kishore.
Yes. So I'll put it on full screen. So, okay. All right. So once again, welcome you all to this edition of Excitement of Research and the funnel into the long summer internship programs, right? So I would like to basically use this opportunity to excite you on research into algorithms and what I call as algorithm engineering, really, to illustrate some of its applications and hopefully see how one can participate in this research also. Right? All right. So I normally focus significantly on graph algorithms, and this is not for no reason at all. If you observe, there is a lot of data that we generate today, and much of the data is kind of relational in the sense that you could actually represent it in the form of a graph. Some vertices, some edges, maybe weights, maybe other manifestations in the graph. Many questions then turn out to be questions on the graph, right? For example, does the road network that we look at have good amount of redundancy, right? For example, if we want to go from point A to point B, how many routes are there? Are there issues such as, suddenly there is road work at one point and you cannot reach from point A to point B anymore. Is that likely? Right? How many such disruptions can exist actually? Right? Or if you look at a social network, for example, you are all possibly participating or actively, looking at Facebook or Twitter or these kind of social networks, right? So you may ask, for example, what is the role of a node in such a network, right? Is it in the middle of too many things, or is it just at some periphery? What is the influence of the node? How much can it really, control the dissemination of information, etc. Right? So similarly, these are of course maybe new age kind of problems, but even other problems coming from optimization, sciences, engineering, all of these can be modeled as problems on graphs, right? So which means that, look, there are a lot of interesting problems with applications, and therefore naturally attracts a lot of researchers to provide solutions to these problems. So what is new, therefore, in the last maybe 2-3 decades is that if you just imagine, okay, look, I know this problem, I know this algorithm, end of story, that view is changing slowly. Why is it changing? Well, multiple reasons. One is that currently we have a good number of very good data sets, right? So for example, you could look at what is the kind of, road network across the country or state or across the globe or whatever, right? Okay, all right. So you have multiple such, data sets that you can run your algorithms on, understand where are the pain points and things like that. Similarly, people also looked at, what kind of data sets make algorithms toil the most, right? So these are called as challenge data sets. These are somehow the toughest instances for a given problem or for a given algorithm, right? So you can ask, if some algorithm finds it very, very difficult to process this particular instance, are there different algorithms? Are there alternative algorithms that can avoid this, trouble on particular data sets, right? So those are called as challenge data sets. Similarly, people also look at benchmark data sets, right? For example, for a given computation, what are the typical, 10 or 20 instances one should try their algorithms on, and getting good performance on these instances is likely to somehow indicate that the algorithm will be doing good across multiple data sets or across instances, right? Okay, so that is also possible these days. Now, the other way to think of it from an algorithmic point of view is, as the size of the data increases, many of the algorithmic questions that are not really important in a different era suddenly start to become important, right? I'll explain that in a minute, coming back to that in a minute, a little later. So how do we at least tackle these problems? What are common across some of these solutions? Well, parallelism is one of the ways to actually address the scale issue, right? Why do we want to do that? Well, remember, when you use a parallel algorithm, you expect to get significant speed up, and therefore the time taken to solve the same problem will naturally go down, right? So in fact, that is so interesting that if you want to look at, how many papers are produced every year on parallel graph algorithms, right? So just search for this kind of keyword in your Google Scholar, and you can see that if you say from since 2020 is when I wanted to study this field, then you'll suddenly look at more than 20,000 papers, right? So the rate at which the area is growing is significant that way. Okay, all right. Now let us now focus only on parallel algorithms and graph algorithms. We want to at least understand what are some high-level challenges. What is keeping people busy, right? Writing all these papers. So there are lots of issues I'll try to mention some of them at a brief, let us say, level of complexity. So when we talk about parallelism, one of the things that come to mind is the ability to process operations or algorithms in parallel, right? So for example, how do architectures do that? How do architectures enable that? What kind of constructs should algorithms use or should programs use? So one of the things is what is called as the SIMD style, which stands for single instruction multiple data. So which means that, basically you want to consider that you are applying the same instruction, but on different data sets, and all these, application of instruction on data, because it is happening on different data items, can be done in parallel. That's why it is called a single instruction multiple data. But how do you write your computation to be of a kind which can benefit from this SIMD style of execution? Right, so therefore that requires the design of new algorithms to be able to exploit the features that parallel computer architectures provide for users. Right? The other question is about data structures. We all know about a lot of data structures, binary trees, this kind of hash table, some other fancy thing, whatever, right? Okay, but what happens usually is that these data structures were designed at a time when parallelism is not a concern. It's not even existing. So these are very, very sequential in nature. You want to do some insert or delete on a particular data structure. It will do one step at a time. And it will slow. I mean, if you imagine you will use the same kind of data structures in a parallel algorithm, suddenly you will realize that you will not get the speed you wish to observe in your parallel algorithm. So what it means is that maybe you have to relook at the kind of data structures that you use in your sequential algorithms and make them more parallel friendly, right? Okay. Now coming back to machine level concerns again, of course, the way the computer architectures are evolving, they usually come with a deep memory hierarchy and a good amount of irregularity in the way programs interact with memory, right? So for example, if you access array-like data structures, there are features of computer architecture such as caching and tiling and other things that help you, in some sense that reduce the overall time taken to read off from the memory. Whereas if you are doing something like a linked list where one memory or one data item is in particular memory cell, the other is in some other remote cell in the computer, then suddenly all the techniques that architectures use to do this kind of caching, prefetching, all these things don't work on these irregular data structures. And graphs are one such data structure, right? At least the way we typically store them becomes a bit of concern in trying to figure out how an algorithm or a data structure can be mapped to the memory system of a computer. Another concern that comes up in the design of parallel algorithms itself is, look, the way to think about it at a very high level is we have multiple threads. Each can do certain job or a certain work for us, and work gets done faster this way. But is everybody doing the same amount of work, or is every thread equally likely to stop at the same time, so that our overall execution time is not really a combination of processing and waiting or whatever, right? So this load imbalance is something we have to worry about in general with parallel algorithms, but in particular with graph algorithms also. Okay, so my usual style of putting it 3 dots is to indicate that, look, there are. Oh, sorry, I thought I will use the pen and. Okay, so this dot is like a very, very old style of writing C programs, where you can use the dot to refer to innumerable or basically many things at once, right? I mean, you could expect, if you look at the notation, it says that, look, I don't know how many things are there, but you be prepared for more than one possibility here. So that is like the, kind of challenges we face here also. Okay. All right. Anyway, now you could imagine that, look, I can access parallel computers. I have all these things available today. Will it really mean that many algorithms become very, very easy to execute on today's computers? Well, not really true. So there are lots of graph computations which are very, very time consuming, even at that scale, right? For example, I would refer to centrality metrics as one possibility. I'll define the problem in a minute, but the typical algorithms that we have today for finding or for computing the centrality metrics, they require work that is in the order of number of edges times the number of vertices of the graph, right? So what is a big problem with that? Well, imagine that, look, I said the size of the data sets are very huge today. In fact, Shobhadeep showed that we are only talking about the tip of the iceberg really when we look at many of the things at a Google scale or whatever. So imagine you are trying to work on a computation of a graph that is about 1 billion vertices and 100 billion edges. These are not uncalled for numbers in today's research domain. You can easily come up with multiple data sets that actually cross this barrier of 1 billion vertices actually. Right. Okay. Now you apply your back of the envelope calculations. You want to find the centrality score of such a large graph. Then you will require roughly of the order of 10 to the 20 computations, right? Basic operations. Now even a petaflop supercomputer will still require 10,000 seconds to solve the problem actually. Of course, this is a very, very rough back of the envelope calculation because it's assuming a lot of things, including complete access to the supercomputer, no other inefficiencies introduced in the process and things like that, right? So what all this means is that even though we still have a lot of challenges in designing algorithms, implementing them on parallel computers, maybe there are a few missing pieces also, right? I mean, what are these missing pieces? Let us try to understand at least one of them. I would posit that, look, we should also look at algorithm engineering to bring the theoretical advances in algorithms to be more practical at a machine scale implementation. So what does that mean? What is algorithm engineering really? Well, if you study a first course on algorithms, usually you do these two steps, right? They will show you how does this Dijkstra's algorithm or a Kruskal's algorithm is designed, or something using dynamic programming or whatever methodologies you have. They will tell you that, okay, look, because of these reasons, this is the time complexity of the algorithm. It takes a worst case of so and so time. And that's where we stop usually. Very few, maybe the eager ones out of the lot will ask or will try to say, okay, look, let me write the program and see what happens in practice. So you will try to do an implementation of that, right? In fact, to me, the real process of designing an algorithm does not stop at this step also, right? So we need to do a lot of experimental analysis to try to understand how this algorithm works in practice, right? Why do we want to do that? What are some advantages? If you look at all these, arrows emanating out of this box called experimental analysis, you can understand that, look, this is a good way to actually feedback into our design process itself. How do we do that? Well, many ways.
Are you sharing slides?
Yes. So it's not visible.
Only the front first one is visible now.
Oh, really? I see. Oh, wait a minute. Let me try again. We should have mentioned. It could be because, when I switch it to slideshow, it would have possible. Do you see it now?
Yes.
Okay. All right. And if I flip, do you see it?
Yes.
Okay. All right. maybe during this moving it to slideshow mode, something didn't really connect. Okay, all right. So yeah, I'm on this picture where I said, look, there are maybe the first two boxes that correspond to the typical steps we study in a first course on algorithms. And the third step is where, some of the, eager ones want to possibly do an implementation and see what happens. And then, the last box is where we are more, interested in this domain of algorithm engineering. The idea is to use experimental analysis to feedback into the other steps that we typically do before, right? For example, by observing how the algorithm runs in practice, we may be able to get more insights into the design process itself, or we can even understand what are some bottlenecks that the algorithm faces and what are some heuristics to avoid these bottlenecks, right? So for example, if we realize that, look, this algorithm spends a lot of its time on a particular step or two, can we really say that, look, I want to redo that step in a different way? Right? That is what these, heuristics can help you with, right? So in other words, we are able to basically see that this algorithm design and implementation process is a closed loop, right? And for example, you start from here, you do these steps, and you could actually, go back to that step also, right? So this picture, part of it is credited to Italiano for his algorithm engineering slides. Okay, all right. Now, to understand more about this algorithm engineering, I would like to think of it as a set of three possibilities, right? And of course, there may be many more over time, but here is the first three techniques that, at least we think of as important ones in the algorithm engineering process, actually, right? So for example, we can think of techniques that reduce the volume of computation, right? So these immediately translate to practical gains in efficiency, right? Okay. Or as I mentioned briefly before, can imagine that in your experimental analysis of the algorithm, you identify one or two steps that consume a lot of time. Then you can possibly redesign those steps to reduce the impact or reduce the time that the algorithm spends on these steps. So we'll call it as a reinterpret technique. The other thing is basically reuse. Here, the idea is that, look, the goal of an algorithm may be to compute a particular function at every vertex or at every edge or something like that, right? For example, you may say, I want to know what is the centrality score of every vertex. So the computation is about centrality score, but you need to do it for every vertex. Right. So this reuse technique will say that, look, there are a bunch of such functions you will have to apply on some vertices. For other vertices, you may possibly reuse what you computed a priori, and you don't have to really do the whole computation from scratch. So that will at least make quick progress on a certain fraction of the input or a certain fraction of the computations, compared to doing the same thing at every vertex or at every input, really. Right? Okay. All right. So what we'll do is going forward, I'll try to show you how these techniques can help us, at least seed the algorithm engineering process for one or two problems, actually. Okay. All right. Okay, so before we go there, let me just try to illustrate those three techniques in a couple of pictorial slides. So when we look at reduce the volume of computation, what we want to do is that maybe as a generic technique, we'll try to reduce the size of the graph, right? So from this input graph, we're going to maybe this graph size, right? And basically, we may be actually computing. Basically, this is our function or our algorithm. We are not applying it on the entire graph, but we apply it only on the on the smaller graph edge, right? So of course, it is possible that, look, you may not be getting the same final output anymore because you are not computing on the entire graph, you are computing only on a small graph edge. So we'll possibly introduce some post-processing steps to get to the same kind of output as if you applied the computation on the entire graph. So the hope is that as the size of the graph reduces, our compute will take lesser time, and post-process usually should be quick enough so that the total time spent here is really much smaller than what you would do when you use the computation on the entire graph GX. All right. So that's why we call it as a reduce technique, where we are simply applying the same algorithm on a smaller graph. Actually, that's why we call it as the reduce technique. All right. So here is what reinterpret looks like. This is what you would do, in a traditional or a standard way. This is what you did in the reduce way. So here reinterpret allows you one more possibility. It is that, look, some step may be, very, very time consuming in our algorithm. So I would possibly replace that step with a different, step, right? So what does that mean? Maybe I will do some, processing or a pre-processing here. I will get some approximate, let us say subgraph or whatever. I will call it H dash, and I'm computing on that. Right, so this is where we are replacing some expensive steps with maybe inexpensive, steps otherwise. So naturally, it is likely that you may not get a good answer anymore. You will get some partial answer, and you need to basically do some post-processing to reach to the same answer that you desire on the original graph. Right, so that means that you do multiple of these, processes, right? To basically reach the same answer, but using different algorithms, using different steps, which we hope or which we expect to be less expensive than any of the other steps, actually. All right, so that is where we call it as a reinterpret, because we are saying that, look, we don't want to do the same thing that the traditional algorithm suggests. We'll do something slightly different, expect that we'll end up with a slightly incorrect answer or a partial answer, and then try to recover what it will lose by using some post-processing steps. Okay. Reuse, as I mentioned before, basically we want to apply some, some function like compute on each of the vertices, right? So imagine we did it on all these green ones already, but we don't know what is the answer of compute on these, black colored vertices, right? These are unprocessed yet, but hopefully we'll be able to obtain the output of applying compute on a vertex Y as a function. This is what we have to provide now as a function of the result of applying compute on a bunch of other vertices, right? So this U, V are already processed. We know what is the result of applying compute on them. You use a different function F to put together, to compose the output on U, V, etc., to know what will be the output on Y. So that is what we call as a reuse technique. So this is just in pictures. Now I will try to give you a good example on how to use some of these techniques, maybe even in combination also, so that we can actually start to look at algorithms that do better than traditional, algorithms actually. Okay. All right. So I'll use these techniques on this problem called betweenness centrality. Again, it's a problem where you are trying to obtain a metric for every vertex. So let me explain the formula quickly. So on the numerator here, we are looking at the number of shortest paths from S to T that go via a vertex V. Right. So in this case, there are 4 shortest paths from S to T, and 2 out of them 4 go through the vertex V. All right. Okay. On the denominator, basically, we're looking at the total number of shortest paths between S and T. So that is 4 here again. Okay. Now, for a vertex V, we add up over all possible S and T, these kind of fractions. That is where we get the betweenness centrality of a vertex V. All right. So in fact, if you imagine this is S1 and T1, so then you do the same thing for S2 and T2. So maybe none of these paths go through V. So the contribution of S2 and T2 will be 0 out of 3. Then you can think of another S3 and T3. Maybe one of the 3 goes through V. So the contribution is 1 over 3. So you add up all these fractions for all the S comma T pairs, then you get the betweenness centrality of the vertex. As you can notice, the score for a vertex V is very high if V is in the middle of many shortest paths across many pairs of vertices, right? So that is where it is useful in social networks also. These nodes become central to the network, right? Because they are sitting across multiple shortest paths, right? These kind of metrics can be used in studying, let us say, epidemiology and the spread of infection also, right? So who is kind of, maybe spreading it to more people, right? I mean, because of their connections to many people, maybe, you can look at who are the super spreaders, so to speak, actually, right? Okay. All right. Of course, those were the terms we were talking 2 years ago, 2.5 years ago, but hopefully now with the pandemic behind us, we don't have to worry too much about the practical or the real world super spreaders and all these things, but it is good to be prepared and to study all these notions, actually. Okay, all right. Right. Now, naturally, as we mentioned before, this kind of computation is a very time-taking or expensive computation, and we just wanted to see how to do it in parallel and faster, right? All right. Okay. So here is one of the steps we have used. This is about the reduce step, actually, right? So what we do here is that we'll try to reduce the input graph to a smaller graph. All right. So how do we do that? Well, we will basically remove every node that has a degree 2 in our graph. So we just shortcut those things. And so you can imagine the resulting reduced graph does not have the vertices F, G, and B anymore. We just remove them by some means, right? Okay. Right. Now, our technique says we'll do the computation on this graph. So we did that. This is the output. By the way, for vertex A, the centrality score is 3 because there are 3 pairs of vertices whose all of the shortest paths actually pass through A. So each of these pairs is contributing 1 to the sum. So therefore, the centrality score of A is 3. No other pair actually adds a positive contribution to the score of A. So the score of A is 3 really. Okay, all right. Now, what we want to do is that, look, by using some reduce technique, we'll be able to just compute till here. And by using the reuse kind of technique, we'll be able to fill in the scores for the ones that we did not compute earlier in the reduced graph. Right, okay. All right. So how does that work? Well, before we remove these vertices of degree 2, we'll simply record what is their closest, vertex that has a degree 3 to either side of its, path, right? So, for example, for let us say thing like G here, we'll say, C and A will be the left and right, endpoints for G. For F also, you could imagine C and A are the kind of endpoints we're looking at, and so on and so forth. Right? Okay. So that's how we get a reduced graph. All right. Okay. Now, once we get the reduced graph, as you remember, we'll have to basically compute the centrality scores of vertices in the reduced graph. We'll use an existing algorithm for that. And that algorithm really just does nothing but a BFS or a breadth first search in the original graph from every node in the reduced graph as the source. Right. So basically from A, we are doing a BFS. From B, we are doing another BFS. From F, we are doing another BFS, and so on and so forth, right, in this graph, actually. All right. Now, notice that each BFS can be done in parallel because these are all independent computations. So that's how we use parallelism here. And during each BFS, we obtain these 3 data, points from every vertex, each of which is an array. So one is the sequence array, which shows what is the level number of every vertex according to the BFS from the vertex V. So look at the subscript therefore. The other array stores what is the distance of every vertex from V according to BFS, and the other vertex shows what is the number of shortest paths from V to other vertices. Right? Okay. All right. So that kind of completes that step of the computation. Now we have to see how we can actually reuse and imagine that we look at a vertex V which we removed in the earlier phase, which we did not compute for. But we computed for things like L and R, which have a degree or which have a degree more than 3 and are to the left and right of P, right? So using the arrays S, D, and sigma at L and S, D, and sigma at R, so these look like this, we'll be able to actually fill the array for vertex V, right? In fact, it doesn't take a lot of effort. Just imagine that, in SL, we know what is the sequence of vertices visited according to a BFS from L and from R respectively. So by looking at the distance from L to V and distance from V to R, we should be able to rearrange these two arrays to get what will be the sequence here. All right. So in fact, if this is some DL and this is some DR, so you will know that this will be at a distance of DR plus 1. This will be at a distance of DL plus 1 from V. So you can basically look at which is closer, which will be at a level, closer levels from V, then the next closer and things like that, right? Okay. All right. That way you fill S, and R and D and sigma carefully, right? Okay. All right. So when you apply that, the only hitch at this point is that there's a small hitch here. We assumed that our graph is biconnected, which means that every vertex has at least, or every pair of vertices has at least 2 paths from, 2 paths in the graph. But not every graph that we consider may not be biconnected. So therefore, we need to add one more technique on top of what we have to make sure we extend what we have to regular graphs or general graphs. Right? So there, we can also think of some existing works that exactly did the same thing for us. So we basically break the graph into biconnected components, apply our technique on each of these biconnected components, prepare those reduced graphs, etc., and then fuse the solutions again on these two here and from here to here, basically, right? So you have to take the steps in the backward direction with appropriate algorithms to fill up for what you do in the forward direction, right? So we did all that, and after all this, we do get good speed up compared to existing algorithms. So these are twice as faster usually compared to the other algorithms actually. Okay, so that's the good news about it, and it required a few more other techniques. Maybe I could point you to the paper to see what are all the other techniques we have to throw in to get this kind of improvement. Okay, all right. Now, anyway, so that is a very, very high-level introduction to how you apply these techniques. But what we observed is that these techniques are very generic in nature. You could apply them to multiple problems, and in fact, in combinations also. Right. So, for example, shortest paths, centrality matrix is what we studied today. 2 and 3 connectivity techniques are testing, page rank, year decomposition, other problems on symmetry breaking. So the whole lot of problems that you can study in the context of algorithm engineering on graphs, and use some of these 3, high-level solution ideas to prepare your algorithms actually. And we found that each of these give reasonably good performance, which we can, kind of then indicate that, algorithm engineering is important, right? And you want to just not look at an algorithm and write a program and be happy for it, but you could actually see, are there any chances of introducing techniques that will actually speed up the algorithm in practice. Okay, all right. So maybe with that I will conclude as well. This is one of my last slides. So as I mentioned, these techniques can help improve algorithms for very, very fundamental graph problems also. And naturally, these techniques will be applicable to other domains as well. right? So I want to consider this as parallel algorithm engineering. So that is like the emerging field of algorithm study, and combining algorithms and architectures and parallelism to come up with very, very practical algorithms actually, right? And at least what we observe is that because we did not really tie in a lot of architectural details into our techniques like reduce, reuse, reinterpret, most of these algorithms are platform independent, right? They actually give you good performance across platforms, which is good. For example, you could take them to CPUs, you could take them to GPUs, you could take them to other parallel computers, or even distributed machines. So all of this is possible with this array of simple techniques actually. All right. Okay. So once again, naturally, we do want more people to participate in this journey. So you can always write to me and maybe see what we can do together. Right. Okay. All right. All right. So with that, I will conclude. Of course, this is the last slide. Of course, this is not just one man's effort. A lot of students and collaborators had their valuable contributions. So I just want to acknowledge them also in this talk, and funding sources to make it all happen, right? I mean, you need good resources to be able to illustrate that these techniques work, right? Okay. All right. So with that, I will stop, and I will be happy to take any quick questions. And over to you, Raju.
Thank you, Professor Krishna. We'll just wait for any questions. I think it was really exciting. And for all the prospective interns, when you are here, please do reach out to C-Star and then to the Professor Kishore. If there aren't any questions as of now, we'll move on to the next speaker. So thank you, Professor Kishore.
Thank you very much. Yeah, thank you, and have a great time, everyone. Okay, yeah, hope to see you soon. Yeah, okay, bye-bye.
Thanks. So continuing with the graphs, today we have with us Dr. Charu Sharma, whose research area include machine learning with graphs, and she'll be talking on this topic. She is at the machine learning lab at IIIT Hyderabad, which was one of the most preferred centers for research by interns last year. Dr. Charu has done her MTech in Artificial Intelligence from University of Hyderabad and her PhD from Indian Institute of Technology, Hyderabad. She worked for a brief while with Professor Deepak Pathak at IIT Bombay as a software engineer before shifting base to IIIT Hyderabad. Today, she is with us and she'll be leading with a talk on machine learning with graphs. Over to you, Dr. Charu.
Hi, yeah, thank you. So thanks for giving me the opportunity to talk here. I think it's interesting to talk about the topic. So my topic, I'm actually trying to share my screen. So I hope all of you can see my screen.
Yes.
Okay, thanks. So yeah, so so the topic that I have picked is a more general topic, and I would be mostly talking about the machine learning. I think many of you are already interested and you have seen what goes on in machine learning, but what do we do with graphs in machine learning, and what are the general applications and other things that are there? So yeah, so feel free to stop me or write your questions in the chat. And yeah, so I'll start with the introduction part. So I'll cover what and why are we using graphs and all, and what are the examples, and then what are the goals, what is the main goal which we try to achieve when we go with the machine learning with graph. Then some tasks I would see, if I have time, I would maybe talk in detail about applications or data sets, or I might also skip this because you will anyway get the idea and examples, and then a general perspective on the embedding methods that I would want to cover. So I would start with, I think most of you already know, because in data structures and algorithms, you might have seen graphs, and I think the previous talk by Professor Kishore was also on graphs. So this is just a warm up that, okay, what is actually a graph? So this is an undirected graph that that's being shown here. and then we have the adjacency matrix. That's how we represent graph. Then we also say that, okay, a different version is basically a directed graph. And if we have weights, then we also say that it's a directed and weighted graph. So we can whenever I am talking about graph, you can consider by default the undirected graph unless I specifically mention anything about directions or weights. So this is just to let you know that, okay, by default we consider undirected graphs. And whenever there is a graph word coming, you can imagine something like this. We would see how would we go with that. Then we also say that, okay, when we have this graphs, we also say a part of a graph is a subgraph. So if I take these 4 nodes, I don't know if you can see my cursor, but yeah, if we take these 4 nodes and then edges associated with those, then we say that, okay, there's a subgraph, which is also an important part of this graph. And this is also being used sometimes in finding out whether a smaller graph is a part of the bigger graph or not, and so on. Okay, this is an example of a knowledge graph. So the example that I've shown here, this is an example of just a plain simple graph with nodes like A, B, C, D, E, but what these nodes constitutes to and what are they referring to. So basically, if you go to a real world graph, then we have more information at the node and more information at the edge. And that's why we call it a knowledge graph. So for example, here, a node represents something. So this is Liverpool, this is city, this is a football team. And then an edge is also being represented by with something like Liverpool FC is a football team, and then Liverpool is a city, and so on. You can also imagine a social network on Facebook and Twitter kind of a graph where every person's account is actually a node. And if a person is connected to some other person on with some other account, that means to other node, that means that's an edge. So knowledge graph actually captures entities, types, and relationships. So either here, entities show a node, relationship is an edge, and a type is a type of a node or a edge. For example, just Liverpool is actually a different type of a node, whereas this football team is a different type of a node, right? So this George is actually a person type, right? So there are also different types of nodes also. And so you can imagine that if I am making a graph of Facebook, and I take all of us and every person is a node, then we say that in my graph every node is a person and nothing else. I'm not making any node which is a post or a video or an image. I'm just making a graph where every node is a person. So that is my, like, all the type of nodes are same. So we call that graph as a homogeneous graph. Whereas if we have different types of nodes, like a person node or a post node or a video or a image or something else, or a group is also a kind of a node, then we call it a heterogeneous graph. So in knowledge graph area, there is a lot of work on this heterogeneous graph. And nowadays, if you make a knowledge graph,
Maybe there is a network error.
graphs now are being popular from past few years, especially in deep learning. The methods without graph cannot do. Or if we can achieve something without graph, then why are we using graphs, right? What is the importance here? So basically, the intuition, we are saying that graphs are a general language for describing and analyzing entities with relations and interactions. So what happens is, when you I don't know how many of you have already done some course on machine learning, or you have worked on any project where you deal with some kind of a data set or a kind of a data. So a simplistic data is basically a tabular data. You have a table and you have rows and columns, and every row says that this is one particular data sample. This is another particular data sample, and you have some information there, right? So you have a tabular data, and in machine learning, what do we do? What's the main idea? We find out patterns. We find out which data sample is similar to which other data sample. For example, if you have set of images of dogs and cats, then what all the images would go to the dog category and what all images would go to the cat category, right? So we want to find out the similarity between the similar kind of classes, and we want to cluster them. So this is the thing that we can do even with a set of images. We can do with a tabular data, even with something else also. But with graph, if we represent something with nodes, let's say you have images and you consider these images as nodes, then graph actually gives you a explicit information. So you can do things without graph as well, but with graph you have something which is more than the tabular data or a image data or a without non-graph data, basically, right? So graph actually gives you a more information between the entities and the relations. So that's the main idea why I'm using graphs, right? Okay, that was the motivation behind using graphs. And now with examples, I think I've already mentioned like something about Facebook. So here, this is a social network where we can say that, okay, some person is there who likes something, or some person listening to some song, or likes some food or some channel, and so on. So there are different kinds of node type that you can say that a post or a song or a food or a image is also a node type, and a relation is like liking, cooking, watching, and so on. So all of these are actually a graph. You can try to imagine all these things, even something, whatever you see in the real world on World Wide Web, on social media or anything. You can just try to see what if I make a graph out of it. What does it look like, right? Then it's a bibliographic network. There is another example. There is a very popular example of the data set. So usually when we deal with graph machine learning, we work with citation kind of network. So for example, if you have papers, research papers, so if one paper cites the other paper, then there is a connection between the nodes. So you can have, so we call it a citation network. You can also call it a bibliographic network. So for example, this subfigure A, the first graph, is a co-author homogeneous network. Why homogeneous? Because I was mentioning that if all node types are of same category, like the type is same, then it's a homogeneous. So here, the first one is actually making a graph of only the authors, nothing else, no paper, no conference information, nothing, only the author. So if one author cites the other author based on the paper, then you connect them, right? Whereas the second graph actually is a heterogeneous graph where you can see that there is a paper, and this paper is published in this conference. This author is this person is an author of this paper, and this person is also author of this paper, then also of author of this paper. This person is writing this paper. So there are different types of nodes as well, like paper, conference, some year or something, some authors as well. Right? So we have different types of nodes and also relationships. So this is another example. Then whatever we see on Google, whatever you search on Google, so it can also be a non-graph, but even Google also uses a graph kind of algorithm where whatever you search, they actually build it into a graph, and then they question that graph. They actually find out the output from that graph, like which one is the nearest possible answer to your query. So basically there are also query graphs and a knowledge graph where whatever you write on Google, your query would be converted into a graph, and that graph would be matched into a bigger knowledge graph with Google. So this is another example. Then we have something with bio, which is a protein-protein interaction network, where here you can, so the idea here is if there is an interaction between some proteins, then what is the kind of activities that is going on inside. So it's basically the investigation of the biological activities in the cell. So what is if they interact, if they get combined, then what happens, right? So we can find out the behavior or the properties of that. So this is also kind of it is a huge graph. Okay, so this I have taken from some paper. So basically, it's a molecular graph. So in bio or chemistry, you can have multiple molecules, and each molecule can be represented as a graph. So how do we represent it basically? So one interesting idea is whatever you think about whenever you think about any data and you want to make it as a graph, then you have to think it what should be the node, what should be the edge, what should I represent it with, and what would be my features, like what would be my node features, edge features, and so on. So for example, in this particular molecule, in a particular paper from which I have taken this image, so they have represented node and edge in a different form. So they say that, okay, a node can be represented as simply as adjacency matrix, which all of you already know. But node feature matrix they are making with a different properties like atom type, formal charge, and this implicit some information also. So this is basically if an atom has some property, you can always accumulate everything and make it like a node feature matrix. And apart from that, they are also making an edge feature matrix, which is a edge embedding or information associated with the edge. So they are actually making a bond, a matrix of a bond type. So because molecules have different kinds of bonds, so you can always make the different kinds of features and then use that in your learning process. So these are the kind of the formulation that they have made for molecular graphs, but there are other ways as well. It depends on the problem that you pick and what are the kind of features that you want to. I think in the previous presentation, Professor Kishore also mentioned about centrality on graphs and betweenness centrality and so on. So all these things are also being used. We use those also when we have to come up with a node features or edge features kind of thing. What is the placing or what is the structure of the graph to capture that? Yeah. Okay. Then another example is, okay, what if we go with something like a subgraph, and if we have to find out what is the property of a molecule, then we see, okay, if there is a subgraph of some type, then there's a property. So for example, they say that this carboxyl group is part of all these three molecules, right? And this is acidic in nature. So we can say that, okay, maybe a molecule has some property which is acidic, right? So this is also another kind of example where people find out that if there is a subgraph and there is a particular property associated with this, whether this subgraph is a part of a bigger graph or not. So this is also a kind of a thing that people try to match with. Then there is an interesting area which is called a scene graph. So this is something related to the query graph that I was mentioning. So whenever an interesting example is whenever we write something on Google, right? So let's say, for example, I'm writing a person is sitting on a boat, right? What comes up on Google? If you go in the image tab, you will see so many images of a person sitting on a boat, whether it's in the sea or it's not in the sea or somewhere, right? So how do they extract that, right? So when I'm writing this sentence, they actually convert my sentence into a graph, something like this, and that would be like a query graph. And now when they have different images also, so they also make a graph out of the image. For example, these images, if you look at, so for example, there in the fourth image you see a man, and they are also classifying that there is a shirt. So if you see bounding boxes in those images, you will see a man, arm, racket, hand, pant, right? All these boxes are there. So using this object detection kind of a method, they actually make a graph out of image, as well as a graph out of the sentence, a text. So they are actually trying to connect the text data and the image data, where they are converting a graph out of what I have written on Google and also what is coming out of the image. And then they try to find out whatever is my query, which one is the most similar graph. Now, which one is the most similar graph? They would extract those images related to that graph. So this is also a very popular area, scene graphs, and there are a lot of work on this problem as well. Okay, then there are these code graphs where you will see that, okay, for a particular code snippet, you can actually make it like a graph, and the application here is you can actually find out bugs as well. What is the functionality? How can you detect some problem there, right? So this is also being used. Then graphs also has some applications in 3D area, where a 3D object is being represented with a mesh. So this blue thing, so all of these are actually meshes, but if you look at this blue stuff where you can see properly that there are triangles. So whatever is the connections, there are some nodes where there is an intersection, and if you triangulate all these points, then you get a mesh. But you can always say that a mesh is like a graph. So you can always consider a mesh like a graph and then process it using some graph-based method as well to do anything like a classification or any other different. There are multiple tasks in that. Okay, so these has been this has been some examples that I have already mentioned. Now, graphs for machine learning, what is the thing that we want to do? What is the main goal, right? So the main thing that I have mentioned is when we work with non-graph kind of data set like a tabular data, we obviously find out some pattern. But because we have some additional information like explicit relations between the samples or nodes, so we say that how do we take advantage of this relational structure? How do we, there is some kind of a geometry or some kind of a structure which is there, right? So there are some nodes which make triangles, some make some kind of a cluster, some make some kind of a clique. Clique is a complete graph. So how can we take advantage of that, right? So we say that this graph represents this explicit relationship. So we say that, okay, we explicitly model these relationships to actually get a better performance. So the idea here is the whole idea of graph machine learning, the whole crux is basically, let's say you are given an input graph. Now, similar nodes which are there in an input graph should be close to each other in the feature space, the embedding space. So this output is actually a feature space. This is what we want, right? In machine learning, we learn some representation, we learn some feature, we learn some embedding. So what should be the property of that embedding? The property is if two nodes are similar in the input, they should be closer in the embedding space. For example, the example is if I find out the distance between these two embeddings, that distance should be lesser for similar nodes. If I'm embedding a node here, because here there are these nodes and I am embedding a node, and if nodes are not similar, the distance should be far. The distance should be greater, basically. So this is the whole idea. Here, there's a karate graph, which is a very popular graph. They have, I think, 34 nodes. So there's a real world graph, which was studied from 1972 to 1972. And it was a karate club where there were people used to come, and then there was some dispute. So there were some groups that were there after that dispute. So that is why these labels are there. So you can see 4 groups are there: red, this another color, that's cyan, and then violet, and then green. Now, when you use some graph-based algorithm, you get this kind of an output where you see that all the violets are closer because they share a same label, same representations. They are similar actually, so they share a same label kind of, or some property they share. So similar things are closer, and then different things are far. So that is the whole idea of graph machine learning, that similar things should be closer. Now, this similarity is actually different in different kinds of problem. How do you define similarity? That should be different. Okay, so one thing that I want to mention is how do we when we are saying, I don't know how many of you have heard about graph neural networks, that graph neural networks have come up and you can use graphs for that. And but can we not use any basic deep learning method like a CNN, right? So what is the difficulty which is there? So usually we say that graph is not very straightforward to work with. It is not like an image. So what are the challenges that are there? Can we not use graphs same like an image, or same like how do we use CNN or MLP or something like that, right? So there are challenges. Why there are challenges? Because if you imagine an image is a grid kind of structure where you have, you know, that okay, it's a 200 by 200 image size, and you have pixels which are actually organized. You start with some pixel and they have some ordering, some, right? Now, but with graphs, if I make a graph and if I say that there are 4 nodes A, B, C, D. Now, if you have to write in an adjacency matrix, you can write A, B, C, D. But can you change the order, or can you change the label? Even if you change the label, or even if you change the ordering, the graph would still be the same, right? The graph would still be the same. The property should still be the same. So basically, there is unorderedness in the graph, right? There is no grid kind of structure. There is no fixed structure. The neighborhood is also not fixed. So, for example, let's say the image looks something like this, like this. So, for example, if this is a pixel, there's a pixel, then there are some fixed neighbors, right? Some fixed neighbors to every pixel. But in graph, for one node there might be 2 neighbors. For other node there might be 5 neighbors. So there is no structure, proper structure, or a grid kind of structure. So there are challenges if you work with graphs. And we say that what if we want to use CNNs for graph? So we say that okay, we can use CNN something like this. So you have to make a graph like a grid first, and then you use CNN filters to actually learn the node embeddings. So that's how you can do. But this is a very naive way of doing it. But this is one way. So you can see this is my graph. This whole grid is my graph, and this green is actually a convolution filter, right? So this is one way. But in general, it's not so easy to work with. Yeah, so these are actually the challenges. So that network looks something like this. There is no grid, but images look something like this, and text looks something like this. So it's a one-dimensional, and there's a two-dimensional, but there is no fixed dimension to this networks, right? So no spatial locality in like grids, arbitrary size and complex topological structure. That means the neighborhoods are also different, and no fixed node ordering. So these are some of the challenges. That's why GNN came, and there is a different method to what GNNs do. Yeah. So finally, we say that okay, we have this deep learning for graphs, where we say that there's an input graph, and input graph actually showed 2 types of node. That is why. So it's a heterogeneous graph, and you have, instead of simple CNN layers, convolution layers, you have graph convolutions. Similarly, you also have activation function, dropout, and other things, but the graph convolution is actually a bit different than the CNNs. And then you predict something like whether this node is a drug or this node leads to something else. Okay, so this is one thing. Yeah. So this is same as when I was saying, if you have a graph, you need to find out if 2 nodes are similar, they should be closer in the feature space, right? So if you have heard about this TSNE kind of plot, where you see that same class samples should make a cluster in the TSNE plot or in a feature space. For example, like this hidden layer activations. So if you see all these green, yellow, all these are actually the labels of the node. You can imagine that. And you see that your learning should be so good that all greens, all yellows should actually cluster together. So basically, similar things should be closer, and not similar things should be far away. So that's the whole idea. So basically, our main aim is to actually embed this particular node U in a d-dimensional space. So we need to learn this function f in such a way that similar nodes should be closer and non-similar nodes should be far. That's the main idea of learning a graph network. Right? Okay. So now, what are the kind of problems that we can solve with this with the graph with the graphs and graph neural networks? So there are some tasks like node level tasks. Like for example, if I get some features for this, I can say, okay, this is my particular node. So for example, if I talk about any social network, I can say that this person belongs to this category. This person works in finance. This person works in some other area, right? So every person is a node in my social network, and I can classify every node to some category. So that is my node level task. Then there is an edge level task which talks about whether there should be a link. There should be a link between two nodes or not. This is a classic example on Facebook. When you get this people you may know block on Facebook, how do you get it? You get the recommendation that people you may know. How do you get it? Because Facebook is actually predicting that there might be some mutual friends or something common, and then they would recommend some person to you. So they predict that there should be a link between you two. That means you should be a friend of the other person. So that means this link is being predicted by them, even if you are not connected with the other person, but this is the edge prediction that they do, right? Then community level, that all these people are belonging to some cluster or community, for example, based on some group also, you can say. If some people have joined a particular group, then maybe they are part of some community. And then, so this is basically a subgraph kind of level. And then there are also tasks like a graph level. So graph level tasks are, for example, if you say that you have different molecules, then you can predict every molecule to some category, right? So you have every molecule as a graph. So there are two kinds of cases. One is you deal with only one graph, which is a very big graph like a social network. There you can do node level, edge level kind of task. Whereas other kind of data is where you have multiple graphs, where there you can do graph level kind of task, which is a graph classification kind of task. So these are the tasks that you can perform with graphs. Yeah, so here you have this node classification, predict the property of a node, like I was saying for a social network. Link prediction, whether there are missing links between two nodes, knowledge graph completion, and also similar to like on social media, whether two persons should be connected, or you should follow some other person on Twitter or LinkedIn and so on. Then graph classification is like molecule property prediction. For every molecule, what is the property of that molecule? Clustering is if some people belong to some community, then they should be clustered together. Then there are also tasks like graph generation, where you generate, like for example, in images, you have these generative adversarial network, where you generate new images. Like I think you have seen like something like a deep fake on LinkedIn. A lot of posts are there, deep fakes, where they generate fake images based on whatever model is trained. So can you also create new molecules? Can you also generate new graphs? So that is being used in drug discovery when you discover new medicines, drugs. Then graph evolution is another area where it's a sequential data, and you see how your graph evolves over time. For example, in social network, two people are connected maybe today, or two people are not connected today, but tomorrow they might be friends or they might follow each other, right? So how your graph is actually changing. Your graph would not be similar at every point of time, but your graph also evolves over time. So this is another example of these tasks with graphs. Okay, so this is the thing so far. Okay, so and there are some tasks. So these are the similar kind of tasks, but with knowledge graphs. So with link prediction, whether these two things are connected, this is same as link prediction. This is also a clustering kind of graph, community clustering. This is being used in this customer segmentation. So we do get calls for loans and some insurance policy, and I think all of us get that, something like that, right? Why do we get that? Because the companies actually get some data and then they do some machine learning, they use some machine learning model, and then they find out that based on this person's property as in features, like basically right now, what is the age of a person, whether it's a student or an employee or something else, what is the city, right? And what does the background look like, demographic details, and so on. So for example, if you do a job, you will get more calls on loans. But if you are not doing a job, you will get something else, maybe some other things, right? So they do that, and then they find out, they come up with some list, which is a potential list, that if you call this list, then there might be some people who would buy the insurance or the loan, get the loan. So that's how they do this target marketing and customer segmentation using that. Okay, then this entity matching is nothing but if there is a duplication in the graph, maybe like two accounts are there and so on, then we remove the different kinds of account and so on. So these are particularly the tasks related to knowledge graphs. Then there are some applications which maybe I think I would skip. There are quite a few applications. I think some of these I've already talked about. Okay, so one thing I would like to mention is something like a chatbot. I think all of us know that nowadays the customer service actually provides a chat service where you can chat, and that's actually a robot chatting, or a machine learning model chatting. So they try to find out solution using language model, like using the text, what should be the answer. If that doesn't help, then maybe some person would call you, or you should call the customer service. But first they try to find out. So question answering is also another thing where in this area also a graph is being used a lot. Information retrieval is same as what I was mentioning about the Google graph. You search something on Google, they find out from their bigger graph what is the similar output that should come as a result. This is also same as this. Yeah. Then there are some data sets that I will quickly mention. These are some node embedding data sets that usually people work with. In most of the papers, you will see these data sets, some names. And these are graph embedding data sets. So you can see that these are mostly like either IMDb movie data set, or it's more like a protein, enzyme, something related to bio, because there are more like a molecules, right? Here, all these are this is citation network. This is also something related to medical publications. There's a Reddit blog that you see. This is also wiki, and this is protein-protein interaction network. So these are some popular data sets. In knowledge graphs also, we have data sets like Freebase, Wikidata, DBpedia. All these are massive, bigger, very, very big data sets. And there are papers, mostly people use these kind of data sets in there. Okay, I would like to skip this. Yeah, now I think the last thing that I would want to mention is, now we have seen that the kind of the data, what are the applications and so on, but now what are the kind of methods that we use for learning, for the machine, to actually get the better representation. So there are quite a few methods. So some methods which was like centrality on graphs, which was mentioned in the previous talk. So those are actually a traditional methods. Those you can actually compute by yourself, like those are mostly like a handcrafted features. But after those traditional methods, the method which came into picture, and then many people have used that, those are this node representation feature based methods, deep walk and node to vec. These are actually random walk based models. So previously traditional methods used to be there, which people used to use a lot. After that, these were the most famous ones, deep walk, node to vec. And after these, GCNs and graph convolution, graph attention networks came. There are a lot of work on GNNs. And in parallel to these GNNs, because GNNs are also like mostly for something like a general graph, not particularly for knowledge graph. You can use for knowledge graphs as well, but this is general for all the kinds of graph. Whereas for knowledge graph embeddings, there are other non-graph and graph-based models, which is like Transc, Transr, and graph-based models, which is an extension of this GCN, which is a relational GCN, where you also aggregate the knowledge graph information. So these are basically the methods. So this is the state of the art which is there in this area. Okay, so this is most likely the last slide that I have. I want to give you the general perspective on the GNN. What is the idea? Why do we use GNN and all? So the general perspective is the general idea. How do we capture information in neural network, in graph neural network? So the thing is, we have a graph for a particular node. How do we train the network, and how do we learn the embeddings? So for a particular node, the main idea is a representation of a node is being shown by its neighborhood, right? So if I want some information from a particular node, this node would be represented by its neighborhood. There in the node's neighborhood, is we are being represented by our friends. So those are the things. So that's the thing, same thing that is being used here. So the main thing is, for example, if this is a node A, the three neighbors are B, C, and D here, right? So neural network actually makes something like this graph, like a computation graph. We call it a computation graph, where if a node A is there, then the neighbors are B, C, and D. Now for B, the neighbors are A and C. For C, the neighbors are A, B, E, and F. And for D, the neighbor is A, right? So this is the kind of a graph that is being used in the neural network, that is being computed in the neural network using the original graph. So what do we do here? We would take information from A and C, which is the neighborhood of B, and pass this information to B. Now, whatever information B has, this is the feature of B right now, right? Then from B, C, and D, all the information would be taken, and this would be passed to A. So a node is represented by its neighborhood. So we call it a message passing scheme, where we say that a message is being passed from every neighbor to a node, right? So a node is being represented from its neighborhood. So this is the whole idea of GNN. There is a lot more to it, but I think I would stop here. If you have any question, please feel free to ask or put in the chat.
Yes, thank you, Dr. Charu. There are two questions on the chat.
Okay.
I'll read it out for you.
Yeah, okay. Otherwise, I can also take a look at it. I'll just stop sharing. Okay. How graphs are more useful than tabular or other structured data? Yes. So as I have mentioned that tabular data, in tabular data or in image data or any other data, we always find out the pattern. So it's basically like a pattern matching in machine learning, that okay, which image is similar to which other image, or which row in the tabular data is similar to the other one. Similar is the case here. You can find out patterns here, but if you see carefully that in a graph you have nodes which represent your row in a tabular data, right? But we are also explicitly mentioning the edges. So that means we are explicitly giving additional information that there is some relation between these rows in the tabular data or between these nodes in the graph, right? So there is more information than what we already have. So that's the advantage of using the graphs. That's the main idea. So we have better information. That is the answer to that. Does AI take like ChatGPT uses these concepts to optimize? Yes, I can share the PPT. I will share that. Regarding the question on ChatGPT, I think yes. I think I'm not sure. I have not read anywhere that what are the kind of models that they are using. So I think they are using language models and all. But even in language models, people use graphs a lot nowadays. I think in every area the graphs are there. So if not, so the answer would be if not directly, but indirectly they might be using it. Okay, yeah, thank you. So, any other question?
Thanks a lot, Dr. Charu.
Dr. Charu, I have a question.
Okay, go ahead. Yeah.
So how did you reach to the point to start your journey with graph machine learning? Like, how did you get to know that this is the thing that interests you, and what led to it?
Yeah, so that's actually so there is no right answer to it. Yeah, but the main thing is I think in research you need to explore, and so I was working on something like geometry of the data and geometric deep learning that I work in, and there you have the 3D and the graph data because it is beyond the images and tabular data and all, right? So that was my interest, but I eventually landed up by exploring, I would say. Yeah, I explored a lot, and then I was also interested previously in graph theory during my masters. So I did read all of those things, but yeah, it's definitely about the interest. But I think do not stop exploring. That's the main thing. Yeah.
Thank you so much.
Yeah.
Thanks.
Okay. Yeah.
No more questions. So let's stop here. Okay. Thanks a lot.
Thank you. Yeah. Okay. Bye.
So we'll take out from there, and then, as we promised, this is the question Q&A session on internship. Any questions that you have, but before that, Rifna will be sharing with you a small questionnaire about which carries some lightweight questions on the sessions that you have just attended. So request Rifna. Yes, she has already put it out on chat. So are you able to see the question on chat? Google form. So we'll give you another 4 minutes, maybe at till 12:40, just to see how well you have understood the concepts, and also to make this as the third screening process. Yes, if you are all done, maybe one more minute and then we'll start. If the answer is you're not sure, you can put a no there. That's okay. What we need is a response. Okay. So Rifna, you can just toggle it off. And now let us look at the questions that were being put up. Okay. One is number of students, interns that might be selected, and when is the results of second round. About relieving, okay. Can I get time till Monday? No, it should be now. When are the results going to announce? Yes. Can someone please tell me which form are you talking about? I was disconnected. Okay. So that's it. So now the part is, I told you earlier, this is a tricky state and we want to be in your full attention. Okay, at every stage till you are selected, okay, you are not there. Okay, only till you get the final call, you can confirm that it is there. And we expect the same thing when you are inside the campus. You need to be in your full attention, and then you can't miss out on any silent features. Okay, so this was a surprise third round of screening that we did, and then we wanted to see who are the students who are really interested and keen to learn things like that. Okay, others might be just taking it as another opportunity. Okay. Okay, so the questions that you have asked is about the first part, which is about the second screening test results. Okay, so second screening results were descriptive in nature. You were asked to, for those who qualified the first round and whose names or emails were there, you were asked to pick up 2 papers and put up a response. So many of you have did it. Congrats and thanks for it. And some of you have relied on third parties like ChatGPT for preparing responses. So that's also in our notice. So we are not supposed to see how you let others think for you. We are supposed to see how you think for yourself on those questions. Okay, so that's why we discouraged ChatGPT at this level. Not that ChatGPT is bad for research. You can use them for your research, but when we are looking at asking for your capabilities to analyze a paper, we are looking at your capabilities, not ChatGPT's capabilities. Okay. So which domain, that's a nice question. Karthik is asking which domain will we work. Okay. So you have already given us the preference about your domains, like whether it is coding, whether it is on other research aspects of research, or whether it is on publication, on patents, on product developments and stuff like that. So we'll put out all these details to the faculty members at IIIT who might be there for the summer and who will be finally guiding you for research. So, and it will be there up to them to select you. Okay, so we will not be able to come up with a firm number. Last time it had been pretty good in the initial phase. Teachers picked up a few numbers and then we told them that there are still more candidates waiting, and then they picked up large numbers. And then we also had students who said they would like to do in the online mode, not ready to come to campus. So again, the number extended. Okay, so we had a hybrid mode last time. People who actually came down to campus, and then also students who did it from their respective campuses or homes. Okay, so it was online plus in-campus mode that we had last time, and it went off pretty well. So the same thing will be done this time also. We'll ask teachers to pick up, and then by teachers I mean the research groups. And once you are there in these research groups, there are all around 25 research centers here, plus translation and a software development team at Hub. So where we had large numbers last time. So those people will be doing, those who are selected for translation and for coding, they'll be doing purely the coding part. The others will start their journey with every stage of actual research work. Okay. Has the selection process started? Yes, the selection process has almost come to an end now. Okay, so this is today's quiz is the last in that series. And then now we'll shortly announce, okay, and then now the teachers, you will put the shortest list to the teachers for those who have qualified, and then teachers will contact you directly, okay? So my request to you at this point is, do not treat any centers, do not wait for just a call from machine learning centers like Machine Learning Lab or CVIT to join, for you to give the nod. If it is any center, just say yes. Last time we have seen students who said no to particular centers, they were not picked up by other centers. Okay, so that is there. And as far as the research internship program is concerned, I would like to mention a couple of points here. The research internship program is to, now you have seen some of the lectures today. This is also part of internship program. You will have a series of lectures as well as a series of tutorials in Srishti 2023, and that is the research internship program. Okay, so where we'll be exposing you to the basics as well as some advanced topics in all the research centers here at IIIT. When I say research centers, these are again the cutting edge areas where solutions are sought for, and solutions from where solutions are highly valued at the international level, because you find large number of publications coming out of these centers. So that is it. So our focus will be to give you focused lectures on fundamentals as well as advanced on topics that each of these centers consider to be important. Okay, so that's one part. Also, we have our coordinators with us, Rifna, Faima, and Mithuna. They will be giving you, sharing you with tutorials, which will be the hands-on session as part of this research internship program, mostly relating to experiments on machine learning. Okay, so we'd like to see that at the end of this internship program, you are almost as good as some of the teachers who presented their topics here. Okay, so that's the research internship program. So for this, we have a constraint that we cannot call all of you to IIIT Hyderabad to stay here, because we have limited number of accommodation with us. And we can't also have a large group here, because there are also simultaneously there will be other workshops and student groups running parallelly. So there is a limitation on the number of people we can have physically inside the campus. Okay, so for all of those who are not there physically, we will try to see how to extend these lectures, okay, which are tutorials, which are part of these history programs to you, so that you can attempt it while sitting in your homes. Okay, for some of you who might find it very difficult to travel, okay, you can still, even though pandemic is behind us, it is still not completely behind us. So for those of you who want to study sitting in the comfort of home in summer this year, you are also welcome there. But there is a condition clause attached with it. That is, at the end of every class and tutorial, you will find a small questionnaire coming to you. And if you are not qualifying in that questions, you will not, the next set of questions and the invite for the next session will not be there reaching your email. Okay, so it's a very strict process. We'll be gradually eliminating the students who feel they have other serious interesting to do. It's not that internship is essential for life. For those who feel that, they have serious other engagements to do and you want to drop out, you are welcome to drop out. Okay, so we'll carry on with those limited set of students who are there with us throughout the internship program, and at the end, all those who complete the internship program will be given the certificates. You will also be part of our extended family of students, where we'll inform you of all the future programs that are going to be conducted at IIIT, and we'll also give you invitations for that. Okay, so this is what I have to say about Srishti in general. Now, after this, are there any specific questions?
Yes, sir. I have one query. Actually, I submitted that if I'll be able, my institute will be able to release me from 16th May to, 2 months, but I'll be free from, I think, around 27th. So I felt it no is in hurry, but but if I'll be able to join around 27th, then I'll.
That's okay. We'll again query you before start of the program. Okay, so by early May, I'll be sending out this query once again. I'll be giving you the final. If you are selected by teachers, we'll send out the list we'll publish that list. You can produce that list to your professor and then see whether you can be relieved. Your institute is relieving you. If you want us to speak to one of your professors, that's also welcome. Okay. So I'll reach out to your professor.
So sir, if I felt no as the, response, then it won't affect my selection procedure.
Yes or no is no, you'll not be able to do such long-term predictions. We are all aware of it. This is just to check your keenness. That's all.
Okay, sir. Thank you, sir.
Okay. How are the further studies opportunities? Further, who is asking this? Yes. Yes, please. Yeah, somebody is asking question. Yes, please go ahead.
Sir, actually, due to my unstable net connection, I'm not sure whether the form got submitted. So, can you what is the procedure if it did not get submitted?
Did not get submitted. Okay, we'll leave it to that. Okay. Any other? I think Rifna will be able to tell you. You can communicate with Rifna. She will be able to tell you. Further opportunities, student studies. Yes, as I told you, studies not just joining for PhD and MS programs. That's there. You will be invited for all the special programs that are there, which is the most exciting part of it. Which are done. Many of them will be in-campus programs, and there will be also CVIT summer school is there. So if you are deeply interested in pursuing the contents of machine learning through summer school, you will be invited. Okay, but you'll have to show that you are interested, and then internship is one such opportunity to show that you are actually worth it. Okay, so there will be, as I said, there will be evaluation, continuous evaluation for all the learnings that you will be exposed to, and that will be taken as a measure of your seriousness at IIIT. Well, last year we also had a couple of conversions. That means students who do their internship, they join specifically to get enrolled for their MS programs. And then the other way of joining MS programs is by qualifying an entrance examination, which is physically a tough one. But this is a smooth entry where if we recommend, Hub can recommend certain seats to the professors who will absorb you directly. Okay, so once we certify that you are talented and you are really seeking knowledge, okay, they will oblige us. Process will oblige us. The research centers will oblige us. Yes. Can you please reopen, Hitesh? Is there any other chance for me? But my name wasn't there in the first. Don't worry, Nandini. The fact that you are being called here and then you sat through the entire sessions, tell us about your seriousness. We'll take note of it. Any other questions? Yes.
Sir, actually, I was submitting the form before 12:40, but it was not submitting. But now I am trying to submitting it. It was closed. So, sir, can you actually open it for some time?
You can just pass on your name to Rifna. That's all. What? Okay. The other question? Any other question?
Sir, I clicked submitted at 12:40, but still it is showing that the form is not accepting that is responses.
So you can.
How can I know that my form is submitted or not?
You can just pass on your details, names, and other things to Rifna, Fatima Rifna. Okay, she will take care of it. Any other?
Okay, sir.
Than
through mail.
Through mail, yes. Any other questions? Okay, good. So it went well, I guess. My end semesters, yes. So in certain cases, the other question is whether it starts from the internship program starts generally from mid of May and continues till mid of July. Okay. And some of the institutions will be having exams at this period, maybe at the beginning of the time when we start open the internship or towards the last part. Classes might start early. So all those adjustments will be there, and we are amenable to these variations because no, most of the contents will be extended. Any other questions? Okay. So if there aren't any questions, I thank you all for being here. Let me invite Fahima Vivi to offer the vote of thanks. Fahima, please take over.
Thank you, sir. Hope all the queries have been cleared. Now, I would like to express my gratitude on behalf of iHub-Data for accepting our invitation to attend the 11th edition of Workshop on Excitement of Research. On behalf of all of us here, I thank all the speakers of this workshop who enlightened us with new ideas and food for thought. You have made it memorable with your doubts and queries, and I hope this is to be the best indication for the greatness of this workshop. Once again, I thank each one of you for joining us today. Have a nice day ahead. Bye all.
Thank you, Fahima. Thank you, Rifna. Thank you, Vidina. Thank you, everyone.
Hello, sir. 1 minute. Sir, actually, I tried to submit the form, but I was also unable to submit it, sir.
You can just send an email to Fatima Rifna's email ID.
So, what are the details I need to send? Name?
Your name, yes, and the reason for you for not submitting.
Which one? The second form, right, sir? Because you are telling about.
This, yes, the most recent one.
The one means the about the what you call report on the research papers we have selected that one, right?
No. This one, before the start of this session, there was an exercise for you to fill up the queries that has been posted on the lectures that has been covered today.
Yeah, okay, sir. So I just need to send the details of my name and college.
Yeah, sure. Rifna will check whether you are here or not. He'll check the attendance, and then if you are there, were you there for the sessions, or you just joined now?
No, so I was there for session.
Okay. How did you miss that?
Actually, I haven't seen the chat box. So.
So even I have the same query. Like, should I mail?
Yeah, just send out an email with details.
Yeah, sure, sir.
Yeah, okay.
Okay, right then, bye. See you.
Thank you, sir. Bye all.
Bye all.